Imagine waking up tomorrow morning and the sun simply isn't there. Not hidden behind clouds, not obscured by some rare eclipse, but genuinely, impossibly gone. The sky where you expect to see that familiar golden disk, empty, just darkness and stars at what should be noon. It's the kind of thought that catches you off guard, isn't it? That sudden absence of something so fundamental you rarely even think about it until it's gone. Tonight, we're going to explore that impossible thought together. We're going to imagine what would happen if our sun, that massive ball of nuclear fire that has been faithfully rising every morning for 4.5 billion years, simply vanished, disappeared, blinked out of existence as if someone switched off a cosmic light. Hello and welcome to the Sleepy Astronomer. If this is your first time drifting through the cosmos with me, welcome. I'm so glad you're here. And if you've travelled with me before through the quiet corners of space, it's wonderful to have you back for what might be our most thought-provoking journey yet. Whether you're settling into bed, curled up in a favourite spot, or perhaps lying somewhere under that very sun we're about to imagine losing, I'm grateful you're here to explore this question with me. If you enjoy these peaceful explorations of the cosmos, I'd be so grateful if you'd subscribe to join us for more cosmic journeys. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through space. Now, before we go any further, let me offer you this comfort. The sun isn't going anywhere. Not tonight, not tomorrow, not for another 5 billion years. What we're about to explore is a thought experiment, a what-if scenario that physicists use to understand how our world really works. It's safe here. We're imagining together, and when we're done, the sun will still be exactly where it's always been, faithfully fusing hydrogen into helium, keeping us warm and alive. But here's what makes this question so fascinating. It's not just about disaster or fear. It's about appreciation. When you imagine losing something, you begin to understand its true value. When you walk through the physics of what would happen without the sun, you start to see all the invisible ways it shapes every single moment of your existence. The warmth on your skin, yes, but also the food you eat, the weather you experience, the very air you breathe. All of it traces back to that star we so often take for granted. Tonight, we'll walk through a timeline together. Hour by hour, day by day, year by year, we'll follow what would happen to our planet, to life, to the very atoms in the air around you. We'll discover how long we could survive, what technologies might save us, where we might go. We'll explore the beautiful and terrible physics of a world untethered from its star, floating alone through the darkness of space. And perhaps most importantly, we'll learn what this impossible scenario teaches us about the remarkable, delicate, perfect balance we exist within right now, in this moment, under our faithful sun. So settle in, take a deep breath, let yourself relax into this journey. The question is simple. What would happen if the sun disappeared? The answer? Well, the answer will take us on quite an adventure. Before we dive into what would happen if the sun disappeared, we should probably address something important. This can't actually happen. Not in any way that physics, as we understand it, would allow. And there's something deeply comforting about that, isn't there? The universe may be vast and mysterious and often surprising, but it follows rules. Consistent, reliable rules that we've spent centuries learning to understand. Stars don't just vanish. They can't. Matter and energy are conserved, one of the fundamental laws of our universe. The sun, with its 2 million trillion kilograms of mass, its unfathomable energy, can't simply cease to exist. It would violate everything we know about how reality works. It's rather like asking what would happen if gravity suddenly decided to push instead of pull, or if time started running backwards. The question itself exists outside the boundaries of possible physics. But here's the beautiful thing about thought experiments. They don't have to be possible to be useful. In fact, some of the most profound insights in physics have come from asking impossible questions. Einstein built his entire theory of relativity by imagining what it would be like to ride on a beam of light, something that's physically impossible, yet the thought experiment unlocked secrets about the nature of space and time itself. So tonight we're giving ourselves permission to imagine the impossible. We're going to reach into the fabric of reality and, just for the sake of understanding, pluck our sun right out of existence. Not through any process, not following any physical mechanism, but simply gone. One moment it's there, faithfully fusing hydrogen into helium as it has for 4.5 billion years. The next moment, nothing. Just empty space where our star used to be. Now this is very different from asking what happens when the sun dies. That's a real process, one that will actually occur about 5 billion years from now, and it's a gradual, predictable event. Our sun will swell into a red giant, expanding until it potentially engulfs the inner planets, then eventually shed its outer layers and collapse into a white dwarf. That process takes millions of years and follows well-understood stellar physics. We could see it coming from a long way off. But that's not our question tonight. We're asking something far more sudden, far more dramatic. What if the sun simply disappeared? Instantly, completely, as if the universe had hit a delete key and removed our star from existence entirely. For our thought experiment, let's set the stage precisely. It's noon on an ordinary Tuesday. Pick your favourite season if you like, though it hardly matters for what's about to happen. The sun is directly overhead for someone standing at the equator. Photons are streaming from its surface, taking their 8-minute journey to Earth. People are having lunch, going about their day completely unaware that, in our imagination, their star is about to vanish. And then it does. At precisely 12 o'clock, the sun ceases to exist. Now here's our first fascinating piece of physics. Nobody on Earth would know. Not yet. Not for 8 minutes and 20 seconds. Because light, fast as it is, still takes time to travel. The sun is 93 million miles away, and even at light's incredible speed of 186,000 miles per second, those photons take just over 8 minutes to reach us. This creates the strangest moment in our entire scenario. For 8 minutes and 20 seconds the sun is gone, but Earth doesn't know it yet. The last photons it ever emitted are still in transit, still racing across that vast gulf of space. People are still feeling warmth on their skin from a star that no longer exists. They're seeing light that was emitted by something that isn't there anymore. It's like hearing the echo of a voice after the speaker has left the room, except this echo takes 8 minutes to fade. Think about what's happening in those impossible 8 minutes. Someone in Australia is enjoying a sunny afternoon. Someone in New York is having lunch in a park, feeling that warmth on their face. Solar panels are still generating electricity. Plants are still photosynthesizing. Everything that depends on sunlight is still working perfectly, powered by the ghost of a vanished star, sustained by photons that are orphans now, travelling from a source that no longer exists. There's something almost poetic about this delay, isn't there? The universe's speed limit, the speed of light, means that information itself takes time to propagate, even catastrophic information, even the absence of a star. The universe doesn't update instantly. Changes ripple outward at light speed, and until that ripple reaches you, as far as you're concerned, nothing has changed. But there's another ripple racing toward Earth too, and this one is even more fundamental. When the sun disappears, its gravity disappears with it. And gravity, according to Einstein, isn't a force in the traditional sense. It's a curvature of space-time itself. The sun's enormous mass creates a depression in the fabric of space, like a bowling ball on a stretched rubber sheet, and Earth orbits in that depression, held in its graceful ellipse by that curved geometry. When the sun vanishes, that curvature has to flatten out. The information that the sun is gone has to propagate through the fabric of space-time itself, and that information travels at, you guessed it, the speed of light. Nothing in the universe can carry information faster than light, not even the information that gravity has changed. So for those same 8 minutes and 20 seconds, Earth is still orbiting a sun that isn't there. We're held in orbit by gravitational effects from a star that no longer exists. The Earth is following the curvature of space caused by mass that has vanished. It's moving in an ellipse around nothing, around empty space, around the ghost of gravity. This is the moment when the universe is holding its breath. The sun is gone, but Earth hasn't gotten the memo yet. Not through light, not through gravity. We're living on borrowed time, coasting on momentum and outdated information about the universe's structure. For 8 minutes and 20 seconds, we exist in a kind of cosmic limbo, where our reality hasn't caught up to the new truth of existence. And then the ripples arrive, light and gravity, troweling together at the universe's speed limit, deliver their message simultaneously. 8 minutes and 20 seconds after the sun disappeared, Earth finds out. The sky goes dark, not gradually. There's no sunset, no twilight. At 12:08:20 p.m., in the middle of the day, darkness falls instantly. Total, complete. The kind of darkness you've never experienced, because even on the darkest night there's usually some light scattered in the atmosphere, some glow from the horizon. But this is different. This is as if someone threw a switch. And at precisely the same instant Earth's orbit ceases. Not stops, that's not quite right. We don't suddenly slam on the brakes. Instead, the curve we were following straightens. Imagine swinging a ball on a string in a circle and then suddenly cutting the string. The ball doesn't stop. It keeps moving, but now in a straight line, tangent to the circle it was tracing. That's Earth now. We're traveling at our orbital velocity, about 67,000 miles per hour, but instead of curving around the sun, we're heading straight out into space. We've become in an instant a rogue planet, unmoored, cast adrift, heading off into the cosmic dark at tremendous speed on a journey with no destination, following a straight line that leads nowhere in particular, just out, away, into the endless black of interstellar space. The direction we're heading, that depends on exactly where Earth was in its orbit when the sun vanished. If it disappeared when we were at a certain point, we'd head roughly toward the constellation Virgo, a different point in our orbit, and we might head toward Orion or Sagittarius, or any point on the celestial sphere. It doesn't much matter. Space is mostly empty, and the distance to even the nearest stars is so vast that our chances of encountering anything are essentially zero. But here's something beautiful in all this catastrophe. The moon stays with us. The moon isn't held in place by the sun's gravity, it's held by Earth's. Our satellite, our companion for 4.5 billion years, remains bound to us. As Earth goes careening off into space, the moon comes along for the ride, still orbiting our planet every 27.3 days, still raising tides in our oceans, still hanging in our sky. At least we won't be alone on this journey into the dark. So this is our scenario. This is the impossible thing we're imagining. The sun vanished, Earth freed from its orbit, heading out into interstellar space. Darkness, sudden and complete, and 8 minutes and 20 seconds of cosmic delay before we even knew anything had changed. Now that we've set up our impossible physics, now that we understand what we're imagining, let's explore what happens next. Because those first 8 minutes were just the beginning. The real story, the story of how Earth and life and humanity respond to the loss of our star, that story is just starting. And it's going to take us to some surprising places. Let's rewind for a moment, back to that precise instant, 12 o'clock, when in our thought experiment the sun simply ceases to exist. For the next 8 minutes and 20 seconds, Earth exists in the strangest state of ignorance imaginable. We're living in a universe that has fundamentally changed, but we don't know it yet. Information, even catastrophic information, respects the speed limit. Picture this Tuesday afternoon. It's lunchtime in Sao Paulo, morning coffee in Los Angeles, evening dinner preparations in Mumbai. The late afternoon sun slanting through windows in Sydney. Billions of people going about their lives, and every single one of them is basking in light from a star that no longer exists. They're feeling warmth from a furnace that has vanished. They're seeing by photons that are, quite literally, orphans now, emitted by a parent that disappeared before they completed their journey. There's something almost melancholy about those photons, isn't there? They left the sun's surface 8 minutes and 20 seconds ago, when everything was normal, when the sun was still fusing hydrogen into helium in its core, still supporting the vast convective currents in its outer layers, still being, well, the sun. These photons began their journey in a universe that contained their source, and they'll arrive in a universe where that source no longer exists. They're messengers from a lost world carrying news that's already outdated by the time it arrives. But let's follow some of these final photons on their journey, shall we? Let's pick one at random, a photon emitted from a particularly active region on the sun's surface at 11:51:40 a.m. It's travelled for over 170,000 years, just to reach the sun's surface from the core where it was born, bouncing around in the dense stellar interior like a pinball, gradually working its way outward, and now, finally free, it rockets into space at 186,000 miles per second. At 11:51:40, the sun still exists. Our photon is one of approximately 10 to the 45th photons. That's a 1 followed by 45 zeros, streaming away from the sun every second. It's anonymous, unremarkable, just one particle of light among an incomprehensible multitude. But it's the last generation, the final photons. After this batch, there will be no more. Our photon races across the inner solar system. At 11:52, it passes the orbit of Mercury, though Mercury itself is millions of miles away along its own orbital path. The tiny planet, even closer to the sun than Earth, still has a few more minutes before its own 8-minute and 20-second timer runs out. Well, actually, for Mercury it's more like 3 minutes. The inner solar system is about to get a lot colder, but at this moment, everything still seems normal. At 11:56, our photon crosses the orbit of Venus, the morning star, the evening star, Earth's sister planet. It too remains blissfully unaware. On Venus's surface, beneath those thick clouds of sulfuric acid, where temperatures normally hover around 900 degrees Fahrenheit, there's no indication yet that the universe has changed. The greenhouse effect that makes Venus an inferno will continue for a while yet, sustained by the heat already trapped in that dense atmosphere. And at 1200 hours, The moment our photon has been travelling toward for 8 minutes and 20 seconds, it reaches Earth's atmosphere. Our photon has won a strange lottery. It's one of the last to arrive. Had it been emitted a fraction of a second later, it would never have reached us at all. The source would have vanished mid-journey, and the photon would have become truly orphaned, streaming off into space with nothing ahead of it but the long, cold emptiness between stars. But our photon makes it. It hits a molecule of nitrogen in Earth's upper atmosphere and scatters. This is why our sky is blue, this endless scattering of light by atmospheric molecules. Another few bounces, and perhaps it enters someone's eye in São Paulo. It strikes a rod cell in their retina, triggers a cascade of chemical reactions, and becomes finally vision. Becomes the experience of seeing sunlight. Becomes the last moment of normalcy before everything changes. Because at 12:08:20, the universe runs out of solar photons. Let me paint you a picture of what's happening on Earth during these 8 minutes. These strange, liminal minutes where everything seems fine, but nothing actually is. In Tokyo, it's 1 a.m. The city sleeps under a sky full of stars, stars that are still visible because they're light years away, and their light has been travelling far longer than 8 minutes. Nobody in Tokyo is watching the sun because the sun isn't up for them anyway. They'll sleep through the transition, wake up to darkness, and assume it's still nighttime. It will take them a while to realise that nighttime has become permanent. In Paris, it's 6 p.m. The late afternoon sun, that golden hour photographers love, is casting long shadows across the Seine. Couples are walking along the riverbank. Tourists are taking photos of the Eiffel Tower against a backdrop of amber light. Someone is proposing marriage, probably. Someone else is breaking up. Life in all its messy, beautiful complexity continues, and every single person is living in a universe that's already changed. They just don't know it yet. In Chicago, it's noon exactly. The sun is high, though not quite overhead at that latitude. Someone is eating a sandwich on a bench in Millennium Park, feeling that pleasant warmth on their face that makes you close your eyes and just breathe for a moment. Solar panels on rooftops are generating their peak power output. Photosynthesis is happening in every tree, every blade of grass, every garden plant. The great biological machinery of Earth is running at full capacity, powered by light from a vanished star. Here's a thought that's both amusing and unsettling. During these 8 minutes, solar panels are generating electricity from nothing, or rather from something that no longer exists. They're converting the kinetic energy of photons into electrical current, and those photons were emitted by a star that isn't there anymore. It's like receiving a paycheck from a company that went out of business before the check arrived. The transaction is valid. The energy is real, but the source has vanished. Plants, too, are photosynthesizing frantically, unaware they're about to lose their power source permanently. In those 8 minutes, Earth's plants are converting light, water, and carbon dioxide into sugars and oxygen, just as they've been doing for billions of years. They're running on borrowed time, sustained by the memory of sunlight, by photons that are ghosts of a vanished process. Every tomato plant, every oak tree, every patch of algae in the ocean, all of them are capturing solar energy that has no sun behind it anymore. And people are just being people. Someone is being born in those 8 minutes. Someone else is taking their last breath. People are laughing, crying, arguing, making love, making dinner, making plans for tomorrow. That couple in Paris who got engaged, they're celebrating, imagining a future together, having no idea that the universe's rules just changed so dramatically that the word future has taken on an entirely new and more complicated meaning. There's something deeply human about this, isn't there? We're always living in a universe where we don't have complete information yet. The light from distant stars takes years to reach us. When we look at Alpha Centauri, we're seeing it as it was 4 years ago. When we look at the Andromeda Galaxy, we're seeing it as it was 2.5 million years ago. We're always living with a time delay, always seeing the universe as it was, not as it is. These 8 minutes are just an extreme, compressed version of something we experience all the time. But usually the things we're delayed in seeing don't matter quite so much. As we approach 12:08:20, nothing on Earth has changed. The temperature is exactly what it should be. Weather patterns are normal. The sun's heat doesn't affect weather instantly anyway. There's too much thermal inertia in the atmosphere and oceans. Winds are blowing, clouds are drifting, rain is falling somewhere. The International Space Station is passing over the Pacific Ocean, its solar panels tracking the sun, or rather, tracking where the sun used to be. The astronauts inside are floating in microgravity, possibly looking out the window at Earth below, possibly marvelling at that bright point of light that is, or was, their star. 12:08:10. 10 seconds left. The last photons are crossing the final 1,000 miles. Someone in Brazil is taking a photograph of their lunch, that very modern habit of documenting our meals. The camera's sensor will capture this image using the last available sunlight, though the person won't think about it that way. They'll just think they got a nice shot. Good natural lighting should get lots of likes. 12:08:15, 5 seconds. A student in California is staring out a classroom window, daydreaming during a boring lecture, watching dust motes dance in a shaft of sunlight. This is such a human moment, isn't it? Present in body, absent in mind, watching light do what light does. In 5 seconds, there will be a lot less daydreaming and a lot more paying attention. Nothing focuses the mind quite like sudden, inexplicable darkness at noon. 12:08:19, 1 second left. Somewhere in the Atlantic Ocean, a photon, maybe even our photon, the one we followed all this way, is about to strike a chlorophyll molecule in a microscopic phytoplankton. These tiny organisms, too small to see without a microscope, produce more than half of Earth's oxygen. They're the invisible foundation of our biosphere, and this particular phytoplankton is about to experience what might be the last successful moment of photosynthesis it will ever have. 12:08:20. The last photon arrives. Probably not actually the last. They don't arrive in a neat, orderly queue, but the final wave, the trailing edge of 8 minutes and 20 seconds worth of light from a star that no longer exists, and then darkness. Not the darkness of a sunset, which is gentle and gradual and expected. Not the darkness of a solar eclipse, which is eerie but temporary and comes with warning. This is sudden, total, complete, absolute. In Paris, that golden hour light simply stops. The amber glow vanishes. The long shadows disappear, not because the sun moved, but because there's no sun to cast them. The tourists with their cameras experience something that no camera on Earth has ever captured before. The instant transition from daylight to darkness. Exposures that were set for bright afternoon suddenly find themselves in deep night. The Eiffel Tower, which was glowing in the late afternoon light, becomes a dim silhouette against a sky that's suddenly full of stars. In Chicago, that person eating lunch in Millennium Park experiences something even more jarring. The sun is high in the sky at noon, and then it isn't. Not setting, not hiding, just gone. The pleasant warmth on their face disappears. The light that was making them squint is suddenly absent. And, in perhaps the most disorienting moment of all, they open their eyes and see stars at noon. The Big Dipper probably, visible overhead. Orion might be up, depending on the season. Stars that should be invisible, washed out by sunlight, are now perfectly visible because there is no sunlight to wash them out. The solar panels stop generating electricity instantly. One moment they're producing power, the next moment, nothing. The current drops to zero in the span of a heartbeat. Somewhere, an engineer monitoring a solar farm watches their output. Displays crash to nothing, and for a moment, just a moment, they think it's a technical glitch, a sensor error, a computer malfunction, because solar panels don't just stop working at noon on a clear day. That's not a thing that happens, except now it is. Plants stop photosynthesizing, the great engine of converting light into life, the process that's been running nearly continuously on Earth for over 3 billion years, stops. Just stops. The chlorophyll molecules that were vibrating with captured light energy suddenly have no light to capture. The electron transport chains that were pumping out ATP and NADPH shut down. It's not dramatic. There's no plant equivalent of collapsing in exhaustion. They just stop working, like a factory when the power goes out. Everything winds down to stillness. And in space, the International Space Station completes its transition from light to shadow, except this shadow is different. Usually when the ISS passes into Earth's shadow, it's temporary. 45 minutes of darkness, then back into sunlight as they orbit around to the dayside. But this time, there is no dayside. The astronauts inside, who've probably been trying to contact mission control, who've probably been checking their equipment, who've probably been looking out the window trying to understand what's happening, they finally get their answer. The sun is gone. Earth knows. Finally, after 8 minutes and 20 seconds of ignorance, of living in a universe that had already changed without us knowing, we finally get the message. And now the real story begins. But here's the interesting thing about temperature and heat loss. It takes time. Earth isn't a light switch that turns off instantly. It's more like, well, imagine a brick that's been sitting in the sun all day. When you bring it inside after sunset, it stays warm for hours. It radiates its heat gradually into the cooler air around it. Earth is like that brick, except vastly larger and with much more stored heat. Our planet's average surface temperature right now is about 57 degrees Fahrenheit, or 14 degrees Celsius. That's the baseline we're starting from, averaged across all the oceans, all the continents, all the ice caps, all the deserts and forests and cities. It's a comfortable temperature, the kind of warmth that makes Earth habitable. And it's about to become a cherished memory. Within the first hour after the sun disappears, the temperature drop is noticeable but not catastrophic, maybe a few degrees. It's like a sudden cold front moving in, the kind of temperature change you might experience when a storm approaches. Uncomfortable, yes, but not immediately life-threatening. People start turning on their heaters, pulling out extra blankets, wondering what's happening, but not yet panicking about freezing to death. But the heat keeps radiating away into the atmosphere, which then radiates it into space. This is how Earth normally maintains its temperature. There's a constant balance between the heat coming in from the sun and the heat radiating away. It's like a bathtub with the tap running and the drain open. The water level stays constant because inflow equals outflow. But now we've turned off the tap and the drain is still open. The bathtub is emptying and there's nothing to refill it. By the end of the first day, and this is where we should probably clarify that day has lost its traditional meaning, because without the sun there's no day and night, just continuous darkness. But we're still measuring time in 24-hour increments because old habits die hard. By the end of this first 24-hour period, Earth's average temperature has dropped to around 32 degrees Fahrenheit, 0 degrees Celsius, the freezing point of water. Now this is an average, which means some places are colder and some are warmer. The oceans, with their enormous heat capacity, are still relatively warm. Water takes a tremendous amount of energy to heat up, and it releases that energy very slowly when cooling down. The deep ocean in particular is holding onto its heat like a miser guarding gold. Down at depth, where the water is already cold and dark anyway, things haven't changed much at all. But on land, especially in places that were experiencing nighttime when the sun disappeared, things are getting genuinely cold. Lakes are starting to freeze. Rivers in colder climates are turning to ice. That morning frost you might see on grass on a cold morning. It's happening everywhere now, regardless of the season. The moisture in the air is condensing and freezing, coating everything in a thin layer of ice crystals. And here's where we encounter one of the many ironies of this scenario. Ice, the thing we associate with cold and death, is actually going to become a kind of protector. When water freezes, it forms an insulating layer. Ice is a terrible conductor of heat compared to liquid water. So, as the surfaces of lakes and oceans freeze, that ice acts like a blanket, slowing down the heat loss from the deeper water below. It's nature's way of protecting itself, even in the worst circumstances. But let's not get ahead of ourselves. We're still in the first 24 hours, and there's more physics happening than just cooling. Remember how we talked about Earth leaving its orbit? How we're now travelling in a straight line through space at 67,000 miles per hour? Well, we've covered quite a bit of distance already. In 24 hours travelling at that speed, we've moved about 1.6 million miles from where Earth would have been if we'd stayed in orbit. That's about 6 times the distance from the Earth to the Moon. We're genuinely leaving the neighbourhood now, heading out into the solar system on a trajectory that will eventually take us far beyond Pluto's orbit and out into interstellar space. The Moon, bless it, is still with us. It's still orbiting Earth every 27.3 days, still creating tides in our oceans, though those tides are going to start freezing soon, which will make for some very strange ice formations along coastlines. The Moon doesn't care that the Sun is gone. It's held by Earth's gravity, and Earth's gravity is unchanged. In a way, it's comforting, isn't it? In all this cosmic chaos, at least we still have our companion. We're not entirely alone on this journey into the dark. Now let's talk about photosynthesis, because this is where things get a bit sad for the plant kingdom. Photosynthesis has stopped. Completely. Every plant on Earth, from the mightiest redwood to the tiniest blade of grass, from lush rainforest to sparse tundra vegetation, has lost its energy source. It's like someone cut the power cord to every green thing on the planet simultaneously. But here's the thing, and this might surprise you, the plants aren't dead yet, not even close. Plants are remarkably resilient organisms. They've evolved to handle all sorts of stress, including periods without light. Think about seeds that can lie dormant for years, even decades, waiting for the right conditions to sprout. Think about bulbs that spend months underground in complete darkness before sending up shoots in spring. Plants are patient. They're built for waiting. What's happening in the first 24 hours is that plants are essentially going into a kind of suspended animation. They're shutting down non-essential processes. They're living off their stored energy reserves, the sugars they made during their last day of photosynthesis. It's like when you skip a meal. You feel hungry, but you're not in immediate danger. Your body has reserves to draw on. Some plants will handle this better than others. Desert plants, for example, are already adapted to long periods of stress. Cacti store water and energy efficiently. They can go months without optimal conditions. Tropical plants, on the other hand, used to constant warmth and regular sunlight, are going to have a harder time. Those pampered orchids in fancy apartments, they're probably already looking unhappy. But the bigger issue isn't the darkness, it's the cold. Plants can survive without light longer than they can survive freezing. And as that first day progresses and temperatures drop to freezing, the real die-off begins. Ice crystals forming inside plant cells rupture cell walls. Delicate tissues freeze and burst. By the end of day one, a lot of surface vegetation is already dead or dying, killed not by lack of light, but by the cold. The trees, though, the trees are interesting. A tree is mostly deadwood anyway. The living part of a tree is just a thin layer under the bark called the cambium. The rest is structural support, and that living layer, protected by bark, insulated by the sheer mass of the trunk, can survive cold much better than, say, a delicate fern or a flower. The trees aren't photosynthesizing, but they're not dead yet either. They're dormant, like they are in winter, waiting for a spring that will never come. Deep in the ocean, something remarkable is happening, or rather, not happening. The deep ocean ecosystems that exist around hydrothermal vents, those volcanic cracks in the ocean floor where superheated water rich in minerals comes pouring out, those ecosystems don't even notice the sun is gone. They never needed it in the first place. These are chemosynthetic ecosystems, powered not by sunlight, but by the chemical energy in those volcanic emissions. Bacteria that can take hydrogen sulfide and carbon dioxide and turn them into organic compounds. Tube worms that partner with these bacteria. Blind shrimp, strange fish. An entire community of life that exists in permanent darkness, in crushing pressure, in water hot enough to melt lead, and they're perfectly fine with the new cosmic arrangement. They're like that friend who always preferred staying in anyway, and is secretly relieved when plans get cancelled. For these deep-sea organisms, nothing has changed. The Earth's core is still hot. Plate tectonics are still moving. Volcanic vents are still venting. Life goes on as usual. They're perhaps the only truly safe life on Earth right now, because they never depended on the sun to begin with. They're living proof that life is more flexible than we often give it credit for. They're the ultimate backup plan, though they don't know it. Meanwhile, up on the surface, human civilization is beginning to respond. The initial confusion has probably given way to a kind of organized chaos by now. Governments are holding emergency meetings. Scientists are trying to understand what happened and failing, because what happened is physically impossible, but they're trying anyway. Engineers are assessing the power grid, which is still functioning for now. Nuclear power plants are still running. Hydroelectric dams are still generating electricity. Natural gas power plants are still burning gas. The infrastructure of modern civilization is still mostly intact. But there's a growing awareness that this isn't a temporary situation. When the sun doesn't come back after a few hours, when the darkness persists, when the temperature keeps dropping, people start to understand this is permanent. This is the new reality. And that's when the word survival starts to enter everyone's vocabulary. People are moving indoors. Makes sense, right? If it's getting cold, you go inside where it's warmer. You turn on the heat. You put on extra layers. Basic survival instinct. But some people, the ones who understand what's happening, or who are just lucky in their panic, are starting to think longer term. Where are the places on Earth that generate their own heat? Where can you survive without sunlight? Iceland must be looking pretty good right about now. All that geothermal energy bubbling up from below, heat that doesn't depend on the sun at all. Geysers and hot springs and volcanic warmth that's been there for millions of years and will be there for millions more. Similarly, places near tectonic boundaries areas with volcanic activity, anywhere with significant geothermal resources, these are about to become very valuable real estate. Underground also starts to look appealing. Not just basements, but deep underground. Mines, caves, subway systems, anywhere that's insulated from the surface, anywhere that taps into the Earth's own internal heat. Because here's something people are starting to remember. The Earth's core is hot. Very hot. About 10,800 degrees Fahrenheit hot. That heat isn't going anywhere. It's been there since the planet formed, supplemented by radioactive decay in the mantle, and it will keep Earth's interior warm for billions of years. The surface might freeze, but if you go deep enough, you'll find warmth. You'll find heat that has nothing to do with the sun, heat that's Earth's own, heat that's not going anywhere. It's like discovering that while your house might be freezing because the furnace broke, your basement is still warm because of geothermal activity underneath. You just have to move to the basement. So on this first day, you have a world in chaos, but not yet in collapse. The temperature has dropped from comfortable to freezing, but it's the kind of cold that humans can handle with proper clothing and heating. The plants are suffering, but not all dead yet. The oceans are starting to freeze at the surface, but are still liquid underneath. Infrastructure is still functioning. Society is still organized, though that organization is starting to fray at the edges. And Earth itself? Earth is hurtling through space, a rogue planet now, unmoored from its star, heading out into the cosmic dark at tremendous speed. We've broken free of the sun's gravitational embrace, or rather, the sun's gravitational embrace ceased to exist, and we continued on our way following the law of inertia. An object in motion stays in motion unless acted upon by an external force, and there's no external force anymore. Just us, the moon, and empty space ahead. It's day one of our new existence, and if you think about it, we're doing surprisingly okay, better than you might expect for a planet that just lost its star. We're cold, we're confused, we're scared, but we're not extinct. Not yet. Not even close. The human species has survived ice ages, supervolcano eruptions, asteroid impacts, and countless other catastrophes. We're remarkably good at not dying, at adapting to new circumstances, at solving problems we never expected to face. And this is certainly a problem we never expected to face. But in that first day, as the temperature drops and the darkness persists, there's already a kind of stubborn determination settling in alongside the fear. We've lost our sun. Our faithful star of 4.5 billion years is gone, but we're still here. The Earth is still here, spinning on its axis, because angular momentum is conserved, and there's nothing to stop us from spinning. Orbiting nothing, but still rotating, still giving us a 24-hour cycle, even if that cycle no longer means anything in terms of day and night. We're survivors. We're problem solvers. We're the species that looked at the challenge of surviving in the Arctic and invented igloos, at the challenge of crossing oceans and invented ships, at the challenge of flying and invented aircraft. We're not going to simply give up because our star disappeared. Though admittedly, this is a much bigger challenge than any of those. As the first day draws to a close, not that you can tell because it's still dark, still night, still and always will be dark now, Earth's average temperature hovers around freezing. The surface of the ocean is starting to develop a thin skin of ice. Lakes are frozen solid in most places. The atmosphere is still there, still breathable, still providing some insulation, still carrying weather patterns, though those patterns are getting increasingly strange, without solar heating to drive them. And somewhere, probably in dozens of places around the world, scientists and engineers are gathering. They're running calculations, they're asking the hard questions. How long can we survive? What resources do we have? Where should we go? What's the plan? because there has to be a plan. There always has to be a plan. That's what humans do. We plan, we adapt, we survive. The first day without the sun is ending, not with a sunset, there will never be another sunset, but with a growing awareness of what needs to happen next. The physics are against us. The universe doesn't care about our survival, but we care. And sometimes that's enough to make the difference. The second day is about to begin, and with it, the real work of survival. A week without the sun, 7 days, 168 hours. Though really, days feels like the wrong word now, doesn't it? Days imply daylight, sunrise, sunset, the rhythm of light and dark that's governed life on Earth for billions of years. What we have now is just time. Continuous, dark time, marked only by clocks and the stubborn human habit of organizing existence into 24-hour chunks, even when those chunks no longer correspond to anything real. But let's call them days anyway, because we need some way to measure the passage of time, and days is what we've always used. Old habits, like I said, die hard. Sometimes they don't die at all. They just lose their original meaning and continue on as comfortable rituals, familiar markers in an unfamiliar world. So, 1 week. Let's talk about what Earth looks like after 7 days without its star. The average temperature has dropped to around 0 degrees Fahrenheit. That's minus 18 degrees Celsius for most of the world. To put that in perspective, that's colder than a typical winter day in Moscow, colder than Chicago in January, about the same as a pleasant day in Antarctica. It's cold, properly, seriously cold, the kind of cold that kills if you're not prepared for it. But here's what's interesting, and by interesting, I mean terrifying, but also kind of fascinating from a physics standpoint. The temperature isn't dropping as fast as you might expect. That first day saw a dramatic plunge from 57 degrees Fahrenheit to 32 degrees Fahrenheit. But this second week, the drop is slower. We've gone from 32 degrees Fahrenheit to 0 degrees Fahrenheit in a week, which is still bad, obviously, but it's not the catastrophic acceleration you might fear. This is because of thermal inertia. The Earth is huge. It contains enormous amounts of stored heat, particularly in the oceans. And heat, like most things in physics, doesn't like to change quickly. It's sluggish, resistant. It takes time to radiate away into space. We're not a thin sheet of metal that cools instantly when you remove it from a fire. We're more like a massive cast iron pot that stays hot for hours after you turn off the stove. The oceans especially are acting as gigantic heat batteries. Water has what's called a high specific heat capacity, which is a fancy way of saying it takes a lot of energy to heat water up, and water releases that energy very slowly when cooling down. The deep ocean in particular, those dark, cold depths that were already close to freezing even with the sun, haven't changed much at all. Down at 2 miles deep, 3 miles deep, where the water is already around 35 degrees Fahrenheit, things are pretty much business as usual. Which is to say, dark, cold, and full of very strange-looking fish that never expected to be humanity's best hope for long-term survival. But here we are. The surface of the ocean is a different story. A layer of ice has formed, and it's growing thicker by the day. In the Arctic and Antarctic, where the water was already cold, the ice is already several feet thick. In warmer waters, or what used to be warmer waters near the equator, the ice is thinner, maybe a few inches, but it's there. The ocean is developing a shell, a frozen crust that's sealing in the liquid water beneath. And here's where we encounter another of nature's peculiar gifts. That ice layer, as it thickens, actually slows down further heat loss. Ice is an excellent insulator. It's full of tiny air pockets, and air is terrible at conducting heat. So the ice that's forming because of the cold is also protecting the water beneath from getting colder as quickly. It's like Earth is building itself a blanket, a thin shield of frozen water that says, "This far and no further." The heat beneath this line is staying put. This is good news for anything living in the ocean. The fish, the whales, the dolphins, the countless marine creatures. They're not going to freeze solid anytime soon. The ocean beneath the ice remains liquid, remains habitable. It's getting colder, yes, slowly, gradually, but it's not the instant death sentence you might fear. Marine mammals like seals and whales, which are already adapted to cold water, are probably doing relatively okay. Confused, certainly. Their food chains are collapsing as the surface-dwelling plankton dies off, but they're not freezing. Not yet. On land, things are more immediately catastrophic. Any standing water is frozen solid. Lakes, rivers, ponds, all ice now. The water cycle, that beautiful process that moves moisture around the planet, has essentially stopped. No evaporation from the oceans, the surface is ice. No clouds forming, it's too cold and there's no heat to drive convection. No rain, no snow. Just this strange, static atmosphere sitting heavy over a frozen landscape. The plants, as we discussed, are having a very bad week. Most surface vegetation is dead now. Grass, flowers, crops, bushes, frozen and dead. The trees are dormant but damaged. Ice crystals have formed in their tissues. Bark is cracking from the cold. They're not dead yet, many of them, but they're not alive in any meaningful sense either. They're suspended, frozen in time, waiting for warmth that will never return. But deep underground in the soil, beneath the frozen surface layer, some things persist. Seeds, roots, bulbs, organisms that were already living in darkness. The soil itself doesn't freeze as fast as the surface. Dig down a few feet, and you'd find earth that's still above freezing, still holding onto its heat. Microorganisms are still metabolizing slowly. Mycorrhizal fungi are still threading through the soil. Life underground, which was always hidden, always patient, continues its slow processes. And then there are those remarkable hydrothermal vent ecosystems we talked about before. 1 week later, they're still thriving, still completely unconcerned about the cosmic drama happening on the surface. The tube worms are still tube worming, the bacteria are still chemosynthesizing, the bizarre fish are still being bizarre, they're living their best lives, probably having no idea they're now the most successful ecosystem on Earth. The meek really have inherited the Earth, they just happen to be tube worms living in crushing pressure and superheated water. Now let's talk about what's happening with human civilization, because this is where things get complicated in interesting ways. The immediate crisis has passed, by which I mean the initial confusion, the panic, the chaos of that first day when nobody knew what was happening. That settled into a grim determination. People understand the situation now, or at least they understand enough. The sun is gone, it's not coming back, the temperature is dropping, survival is the only priority. What's remarkable is how much of our infrastructure is still functioning. The electrical grid is still up in most places. This might surprise you, but it shouldn't. Most of our electricity doesn't come from solar panels. Solar power is growing, but it's still a relatively small percentage of global generation. Most electricity comes from fossil fuels, nuclear power, and hydroelectric dams, and all of those still work just fine without sunlight. Nuclear power plants are running normally. They generate heat through nuclear fission, splitting uranium atoms, a process that has nothing to do with the sun. The control rods are still controlling. The cooling systems are still cooling. The turbines are still spinning. In fact, nuclear plants are probably running at maximum capacity right now, because everyone has turned on their heating systems and electrical demand has spiked. Hydroelectric dams are still generating power too, though this is going to become a problem soon. Dams work by water flowing downhill, turning turbines. But water comes from rain and snowmelt, and rain comes from evaporation, and evaporation requires heat. The water cycle has stopped. Eventually the reservoirs will drain and not refill, but for now, this week, they're still fine. The water stored behind dams is still flowing, still generating electricity. Fossil fuel plants, coal, natural gas, oil, are running full throttle. Burning fuel releases heat, which boils water, which creates steam, which turns turbines. This is 19th century technology, and it doesn't care whether the sun exists or not. As long as we have fuel to burn, we can generate power, and we have quite a lot of fuel stored. Coal stockpiles, natural gas reserves, oil in tanks and pipelines. Enough to last for months at least, maybe years if we're careful. So the lights are still on, the heaters are still running, buildings are still warm inside even as the outside world freezes. This is buying us time. Not a lot of time, maybe, but some. Enough to think, enough to plan. And people are planning. Oh, are they planning? The initial response is obvious. Move toward heat sources that don't depend on the sun. Iceland becomes an obvious destination. The island sits on the mid-Atlantic ridge, where tectonic plates are pulling apart and magma rises close to the surface. Geothermal energy is everywhere. Hot springs, geysers, volcanic warmth that's been there for millions of years. Reykjavik, which was already heating most of its buildings with geothermal energy, is probably the most comfortable city on Earth right now. But Iceland is small. It has a population of about 370,000. It can't accommodate billions of climate refugees. So people are looking at other options. Yellowstone in the United States, sitting atop a massive volcanic hotspot. New Zealand, with its active volcanism and geothermal fields. Japan, Indonesia, the Philippines, anywhere along the Pacific Ring of Fire, where the Earth's internal heat is close to the surface. There's also a growing awareness that underground is the way to go, not just because of insulation, but because if you go deep enough, you tap into the Earth's geothermal gradient. The temperature increases about 25 degrees Celsius for every kilometre you go down. So at 1 kilometre deep, it's significantly warmer than the surface. At 2 kilometres, warmer still. You don't even need volcanic activity, just depth. Mining operations become incredibly valuable overnight. Not for the minerals they extract, but for the access they provide. A deep mine is a gateway to warmth. Subway systems, similarly, are suddenly prime real estate. They're underground, they're already equipped with ventilation systems and electrical infrastructure, and they're warmer than the surface. Cities with extensive subway networks, London, New York, Moscow, Tokyo, have a built-in advantage. There's also, and we should be honest about this, a growing realization about who survives this and who doesn't. The people near geothermal sites, the people with access to underground facilities, the people in wealthy nations with the infrastructure to maintain power and heat, they have a chance. People in equatorial regions with no cold weather infrastructure, no heating systems, no warm clothing. Their situation is desperate. This isn't a crisis that affects everyone equally. It's brutally, tragically unequal. But let's not dwell on the darkness. Metaphorical darkness, I mean, since we're already dealing with plenty of literal darkness. Let's talk about the more hopeful aspect of human response, because they do exist. Communities are coming together in remarkable ways. There's something about existential crisis that strips away the petty divisions and reminds people of their shared humanity. Neighbours are checking on each other. Strangers are sharing resources. The social bonds that keep civilization functioning are, in many places, getting stronger rather than weaker. Scientists and engineers are working around the clock. Not that clock means much anymore, but you know what I mean. On solutions. How do we grow food without sunlight? Hydroponics with artificial light powered by nuclear or geothermal energy. How do we maintain oxygen levels as plants die? We don't actually need to, not yet. The atmosphere contains enough oxygen to last for thousands of years, even if all photosynthesis stops permanently. How do we keep people warm? Insulation, communal heating, moving underground or toward geothermal sites. There are even discussions about building something more permanent, not just surviving the next few months, but surviving the next few centuries. Because if we're being realistic, if the sun isn't coming back, and in our thought experiment it isn't, then this is the new normal. We need to build a civilization that can exist without sunlight, a civilization powered by Earth's internal heat, a civilization that lives underground like hobbits but with better technology. It's an audacious idea, an impossible idea really, given the scale of what would be required. But it's also very human, isn't it? When faced with impossible circumstances, we imagine impossible solutions. We dream of survival even when survival seems unlikely. We plan for a future even when the future looks dark. Literally, in this case. The moon is still there, by the way, still orbiting us, still visible in the sky, though now you can see it any time since there's no daylight to wash it out. It's probably brighter than you've ever seen it, actually, because there's no atmospheric light pollution from cities. The sky is darker than it's ever been in human history. The stars are incredible. The Milky Way is visible from anywhere on Earth now, a river of light across the sky that was always there but rarely visible through the glare of our own sun. There's something bittersweet about that, isn't there? We've lost the sun, but we can see the universe more clearly than ever before. The stars that used to be washed out by daylight are now brilliant points against the black. Nebulae that required telescopes are visible to the naked eye. The night sky that ancient humans knew, that true deep darkness studded with countless lights, has returned. Though I doubt many people are stopping to appreciate it right now. Earth, meanwhile, is still hurtling through space on its new trajectory. In 1 week, we've travelled about 11 million miles from where we would have been in our original orbit. That's roughly 45 times the distance from Earth to the Moon. We're genuinely leaving the inner solar system now. Mars is behind us in orbital terms. We're heading out toward the asteroid belt, though we'll pass through that region without hitting anything. Space is vast, and asteroids are tiny, and the chances of collision are essentially zero. The Moon's phases continue. New moon first quarter, full moon last quarter. The cycle continues because phases are caused by the Moon's position relative to Earth and the light source. And we no longer have a light source. But wait, actually this is interesting. The Moon is now always full in a sense because the only light it receives is, well, there isn't any. The Moon is dark. Completely dark except for the faint reflected light from Earth's own artificial lights and maybe a tiny bit of starlight. So the Moon, as we knew it, that bright silver disk, is gone too. It's still there, still massive, still creating tides, but it's visible now only as a dark circle blocking out the stars behind it. A shadow moon, a ghost moon. The tides continue though. The Moon doesn't need the sun to pull on Earth's oceans. Gravity works just fine in the dark. So we still have high tides and low tides every 12.5 hours or so, even though those tides are now freezing in place as the ocean surface solidifies. Picture that. Ice that rises and falls slightly, cracking and groaning as the Moon pulls on it, frozen waves that still remember how to move. It must sound extraordinary if you're standing on a frozen beach, the creaking and cracking of ice under tidal stress, a new kind of ocean music. By the end of week 1, a picture is emerging. It's not a hopeful picture exactly, but it's not complete despair either. We have time, not unlimited time, but time measured in months at least, maybe longer. We have energy sources that work without the sun. We have infrastructure that's still functioning. We have people who are working on solutions, who are adapting, who are determined to survive. The temperature is 0 degrees Fahrenheit and dropping, but slowly. The oceans are freezing, but not frozen. The atmosphere is intact. The Earth's core is still hot. Civilization is damaged, but not destroyed. We're in crisis, absolutely, but we're not extinct, not even close. And maybe, just maybe, if we're smart enough, if we're lucky enough, if we can work together and think long-term and make the right choices, we might be able to survive this. We might be able to build something new, something that doesn't depend on a star, something that draws its warmth from the Earth itself, from the heat of our planet's own heart. It's a slim chance, an incredibly slim chance, but it's more than 0. And sometimes that's all you need to keep going. Week 1 is ending. Week 2 is about to begin. The crisis continues, but so do we. Still here, still fighting, still hoping, against all reasonable odds, that there's a way through this impossible darkness. Because that's what humans do. We hope, even when hope seems foolish, even when the universe has turned against us, even when our star has vanished and left us alone in the dark. We hope, we plan, we survive. At least we try. A year, 12 months, 52 weeks, 365 days, though we really should stop calling them days, shouldn't we? They're just arbitrary divisions of time now, numbers on a calendar that no longer corresponds to sunrise or sunset, or anything celestial at all. But we keep counting them anyway, because that's what humans do. We measure time. We mark its passage. We need to know how long we've been in the dark. 365 rotations of the Earth, then. Because Earth is still spinning on its axis, still completing its 24-hour rotation, even though that rotation no longer means anything in terms of day and night. Angular momentum is conserved, and there's nothing out here in the void to slow us down. We spin because we've always spun, and will keep spinning for billions of years more. It's oddly comforting, actually. In a universe that's fundamentally changed, Earth remembers how to turn. So, 1 year without the sun. Let's talk about what that year looks like, what Earth has become, what survived, and what hasn't. The temperature has stabilized more or less at around minus 100 degrees Fahrenheit. That's minus 73 Celsius. To put that in perspective, that's colder than the coldest temperature ever recorded on Earth's surface, which was minus 128 degrees Fahrenheit at Vostok Station in Antarctica in 1983. It's colder than a Mars winter. It's the kind of cold that would kill an unprotected human in minutes. The kind of cold where exposed skin freezes almost instantly, where breath crystallizes in the air, where metal becomes brittle and shatters. But here's the thing, it's not getting much colder. We've reached something like an equilibrium. The Earth is still radiating heat into space, yes, but slowly now. Very slowly. The oceans, with their enormous thermal mass, are acting as a massive heat reservoir. The thick layer of ice that's formed on the ocean surface is acting as insulation, and the Earth's own internal heat, the warmth from the core, the heat from radioactive decay in the mantle, is bleeding upward, replacing some of what's lost. Think of it like this. Earth is like a house in winter with the furnace broken but the basement still warm. The upper floors are freezing, but if you go down to the basement, there's still heat. The ground floor is cold, but not impossibly cold because some warmth is rising from below. That's where we are now. The surface is frozen and hostile, but it's not the absolute zero of deep space. It's cold, but it's survivably cold if you have the right technology in the right location. The oceans are the most dramatic change to Earth's appearance. They're covered now, completely covered, in a layer of ice. In the Arctic and Antarctic, where the water was already cold, that ice is dozens of feet thick. Near the equator, where the water was warmer, the ice is thinner, maybe 10 to 15 feet, but it's solid. If you were looking at Earth from space and if there were any light to see by, Earth would look like a giant snowball, white, uniform, featureless except for the dark patches where continents show through. But beneath that ice, the ocean lives on. It's cold, near freezing temperatures throughout, but it's liquid. Water at depth doesn't freeze easily because of the pressure. Ice wants to expand when it forms, but under pressure, that expansion is resisted. So the deep ocean remains liquid, remains a habitat, though it's a habitat under severe stress. The food chain has collapsed, or at least the part of it that depended on sunlight. Phytoplankton, those microscopic plants that form the base of the marine food web, are gone. They needed light, and there is no light. The fish that ate the plankton are dying or dead. The larger fish that ate those fish are starving. The whales, the dolphins, the seals, they're struggling. Some have died. Many have died. But some are surviving, at least for now, by adapting their diets, by finding other sources of food. And here's where things get interesting, in that way that nature is always interesting, even in the worst circumstances. The deep ocean, the parts that never saw sunlight anyway, is doing relatively okay. Those hydrothermal vent ecosystems we talked about are thriving. And they're actually expanding in a sense because the nutrients that used to be consumed by surface life are now sinking down to the depths. Organic matter from dead surface organisms is raining down, providing food for deep-sea scavengers. Life is consolidating, retreating to the places it can survive. The surface is becoming a wasteland, but the depths endure. Life finds a way, as they say, though perhaps it would be more accurate to say, life finds the specific narrow set of circumstances where thermodynamics still allows metabolism, and it clings to those circumstances with stubborn determination. On land, the situation is more clear-cut. The surface is dead, almost completely dead. Plants are gone, frozen solid or desiccated by the cold. Animals that depended on surface conditions, most mammals, most birds, most insects, are extinct. The few that might survive are the ones that were already adapted to extreme cold and could find shelter. Some Arctic animals, perhaps, that could retreat underground or find geothermal warmth. But the vast majority? Gone. Underground, though, is a different story. The soil, once you get below the frozen surface layer, is still relatively warm. Not warm by surface standards, but above freezing. And in that soil, life persists. Microorganisms, those ancient and resilient bacteria and archaea that have survived every extinction event Earth has ever thrown at them, are still metabolizing. Slowly, yes, at reduced rates because cold slows chemical reactions, but they're not dead. They're waiting, being patient, doing what microorganisms do best, which is persist. Fungi are still there too, threading through the soil, forming vast underground networks. Mycorrhizal fungi that partnered with plant roots are struggling now that their partners are dead, but saprophytic fungi, the ones that decompose dead organic matter, are actually doing quite well, thank you very much. Lots of dead organic matter available these days. It's a fungi renaissance underground, in a dark and morbid sort of way. And then, of course, there are those remarkable chemosynthetic ecosystems around hydrothermal vents. 1 year later, they're still completely fine. Better than fine even. They've gone from being obscure deep-sea curiosities that most people had never heard of to being the crown jewels of Earth's biosphere. The tube worms are probably very confused about their sudden elevation in importance, assuming tube worms have the neural capacity for confusion, which they probably don't. They just keep doing their tube worm things, unbothered by the cosmic drama, living their best sunless lives. Now let's talk about humanity, because this is where the story gets both darker and more inspiring, often at the same time. The human population has dropped dramatically. We need to be honest about that. Not everyone made it through this year, not even close. The exact numbers are impossible to know. Census taking isn't exactly a priority during an extinction-level event, but it's reasonable to estimate that the population has decreased by, well, let's say a significant percentage. Billions have become millions, perhaps. The people who survived are the ones who had access to heat, to electricity, to food, to shelter. The ones in wealthy nations with infrastructure, the ones near geothermal sites, the ones who could adapt quickly. It's a tragedy of unimaginable scale, but those who remain are survivors in the truest sense. They're the ones who figured out how to live in a world without sunlight, and they're building something new. The survivors have consolidated into what we might call survival zones. Iceland is one of the major centres. The entire population of Iceland, plus quite a few refugees who made it there before international travel became impossible, is living off geothermal energy. Hot springs that were tourist attractions are now critical infrastructure. The island's volcanic heat, which was always there bubbling beneath the surface, is now the difference between life and death. Yellowstone is another hub. The massive volcanic hotspot beneath the park is providing heat for a growing underground settlement. The geysers and hot springs are being tapped for energy. Caves and lava tubes are being converted into living spaces. It's rough, it's cramped, but it's warm, and warm is all that matters now. Similar settlements have formed around other geothermal sites, New Zealand's volcanic regions, Japan's hot spring areas, the geothermal fields of California, Indonesia, the Philippines. Anywhere the Earth's internal heat comes close enough to the surface to be useful, humans have gathered. We're like moths to a flame, except the flame is magma, and the moths are trying very hard not to get incinerated while still staying warm. Underground cities are being excavated. Not cities in the traditional sense, no skyscrapers, no parks, no open sky, but networks of tunnels and chambers carved into rock, lit by electric lights, heated by geothermal wells, or by the natural temperature gradient of depth. Old mines have been repurposed. Subway systems have become permanent residences. Basements have been dug deeper and deeper, seeking warmth from below. It's a strange existence. Imagine living your entire life underground, in artificial light, never seeing the sky, never feeling wind, never experiencing weather, just the constant hum of ventilation systems, the drip of condensation, the warmth of geothermal heating. It's claustrophobic, certainly. It's unnatural in every way. But it's survival. And humans, it turns out, can adapt to almost anything if the alternative is extinction. Food production has become one of the critical challenges. Without sunlight, agriculture as we knew it is impossible. But hydroponics, growing plants in nutrient-rich water under artificial light, works just fine. It's energy-intensive, requiring powerful LED lights to simulate sunlight. But energy is something we have. Nuclear power plants are running. Geothermal plants are generating electricity. We have enough power to grow food, at least for the reduced population that remains. The crops grown are mostly fast-growing, high-calorie plants. Potatoes, soybeans, lettuce, tomatoes. Nothing fancy, nothing gourmet, just reliable calories to keep people alive. The old concept of a balanced diet has given way to whatever we can grow. People eat what's available and are grateful for it. Cuisine, as an art form, has taken a bit of a back seat to not starving. Protein comes from fish farms mostly, tilapia and other hardy species that can survive in controlled conditions. Some settlements raise insects, crickets and mealworms for protein. They're efficient, requiring less space and energy than traditional livestock. Nobody's thrilled about eating bugs, but again, survival trumps preference. You eat what keeps you alive, and you learn to stop complaining about it. Water isn't actually a problem, interestingly enough. We have plenty of water. It's frozen, sure, but ice can be melted. And once you melt it, it's just water. Clean water, even, since the cold has killed most pathogens. Collecting ice, melting it with waste heat from power generation, filtering it, that's straightforward enough. So at least we're not dying of thirst. Small mercies. The atmosphere remains breathable. This surprises people sometimes. They assume that without plants producing oxygen, we'd quickly run out. But the atmosphere contains a lot of oxygen, about 21% by volume, and there are a lot fewer people breathing it now. Even with all photosynthesis stopped, it would take thousands of years for atmospheric oxygen to be depleted by respiration and geological processes. So breathing isn't the problem. Staying warm is the problem. Finding food is the problem. But breathing, that's fine. Psychologically, the adjustment has been harder than the physical challenges in some ways. Humans are solar creatures. We evolved under a star. Our bodies have circadian rhythms tied to light and dark cycles. We have emotional responses to sunlight. There's a reason seasonal affective disorder is a thing. Taking away the sun isn't just taking away heat and light. It's taking away something fundamental to human psychology. Depression is widespread. Anxiety, grief. People mourn the sun like they'd mourn a loved one, because in a sense that's what it was. A constant companion, always there, reliable, warm, life-giving. And now it's gone. Children born this year. And yes, there are children being born because life continues even in the worst circumstances, will never see the sun. They'll grow up in artificial light, hearing stories about the bright ball of fire in the sky that their parents remember. It will be mythological to them. Abstract. A thing from ancient history. But humans adapt. We always do. Communities develop new rhythms, new traditions. Instead of morning and evening, there's shift change at the geothermal plant. Instead of seasons, there's planting cycles in the hydroponic farms. Instead of weather, there's the status of the ventilation system. Life finds new patterns. Not better patterns, perhaps. Not patterns we would choose if we had a choice, but patterns nonetheless. Structure, routine, the things that make existence bearable. Art continues remarkably. Music is played in underground chambers, stories are told. People paint murals on tunnel walls, trying to remember what colour the sky used to be. There's poetry about the sun, elegies for the lost star, attempts to capture what it felt like to stand in sunlight and feel warmth on your face. These creative works are precious now, treasured beyond what they might have been in the old world, because they're connections to what was lost. Their memories made tangible. Science continues too. Research into better hydroponics, more efficient lighting, deeper drilling techniques to access geothermal heat. There's even theoretical work being done on long-term survival strategies. If we're going to live like this for generations, for centuries, what do we need? How do we maintain genetic diversity with a small population? How do we preserve knowledge? How do we keep civilization alive in the dark? Some scientists are even looking outward. Earth is travelling through space, a rogue planet now. Where are we going? Could we potentially encounter another star? The calculations are not encouraging. Space is vast. Stars are far apart. Our chances of passing close to another star, close enough that its light and heat could reach us, are essentially zero on any human timescale. We're travelling at 67,000 miles per hour, which sounds fast, but in cosmic terms is barely moving. The nearest star system, Alpha Centauri, is 4.3 light-years away. At our current speed, it would take over 40,000 years to reach it, and we're not even heading in that direction anyway. So the grim reality is this: we're alone, permanently alone, adrift in the cosmic dark, with only Earth's internal heat to sustain us. There's no rescue coming, no new sun waiting around the corner, just us, our cleverness, and the warmth of our planet's core. But that might be enough. The Earth's core will remain hot for billions of years. Geothermal energy is essentially unlimited on human timescales. If we can solve the technical challenges, growing food, recycling resources, maintaining infrastructure, there's no physical reason we couldn't survive for thousands, even millions of years. We'd be a species that gave up the sun and learned to live in the dark. A species that turned inward, literally, finding warmth in the planet itself rather than in the star we lost. It's not the future anyone would have chosen, but it's the future we have. And surprisingly, impossibly, against all odds, we're making it work. Not perfectly, not easily, with tremendous loss and sacrifice and suffering, but we're surviving, we're adapting, we're continuing. 1 year has passed. The surface of Earth is a frozen wasteland. The oceans are locked under ice. The atmosphere is cold and still. But deep underground, in carved chambers warmed by the Earth's heart, humanity persists. Smaller, certainly. Humbler, perhaps, but alive. Still thinking, still creating, still hoping. Still here. The Earth spins on through the darkness, carrying its cargo of stubborn survivors. We've lost the light, but we haven't lost ourselves. Not yet, not entirely. We're changed, how could we not be? But we're not defeated. And maybe that's the lesson in all this. Maybe the point of imagining this impossible scenario isn't to scare ourselves with thoughts of cosmic abandonment. Maybe it's to remind ourselves of something important. That resilience isn't just about withstanding what the universe throws at you. It's about adapting, finding new ways to survive, drawing on resources you didn't know you had. The sun was always going to be temporary. In 5 billion years it will die naturally, and if humanity still exists, we'll need to have figured out how to survive without it. This thought experiment is just accelerating that timeline, forcing us to confront the question, could we do it? Could we survive without our star? And the answer, impossibly, improbably, seems to be maybe, just maybe, if we're clever enough, if we're determined enough, if we can work together and think long-term and make the right choices. 1 year down, the rest of eternity to go, but we're still here, still fighting, still surviving. That's got to count for something. 100 years, a century, an entire human lifetime in the old world, though lifetimes mean something different now. 4 generations, perhaps 5, depending on how you count. Great-grandchildren who never knew their great-grandparents, separated not by death alone, but by an unbridgeable gulf of experience. Because the people who remember the sun, who felt its warmth, who saw its light, who took it for granted the way you take breathing for granted, those people are old now, or gone, and the world belongs to those who were born in darkness. Let's step forward 100 years and see what Earth has become, what humanity has become, what remains of the world we knew, and what's been built from the ruins. The temperature at the surface has stabilized at around minus 400 degrees Fahrenheit. That's minus 240 degrees Celsius for those keeping track in more sensible units. To put that in perspective, that's colder than the coldest temperature ever recorded anywhere in our solar system before this. It's colder than Pluto's surface. It's approaching the temperature at which carbon dioxide, the gas you exhale with every breath, freezes solid and falls as snow. And that's exactly what's happening. The atmosphere is beginning to freeze out of the sky. Not quickly. Atmospheric collapse is a gradual process when you have as much air as Earth does, but noticeably. Carbon dioxide, with its higher freezing point, is condensing first. At the poles, at the coldest points, there's now a layer of dry ice snow coating the already frozen surface. It's thin, maybe a few inches, but it's there. The atmosphere is slowly, incrementally settling onto the ground like dust. Oxygen will follow eventually. It freezes at minus 362 degrees Fahrenheit, so we're not quite there yet at the surface, but we're getting close. Another century or two, and oxygen snow might start to fall. The air itself will precipitate out of the sky, molecule by molecule, until Earth's atmosphere is no longer a gas but a solid coating on a frozen world. It's a strange thought, isn't it? The air you breathe becoming something you could hold in your hand if you had a very well-insulated glove. But deep underground, none of this matters, because underground, the temperature is stable, comfortable even, by the standards of people who've never known anything else. Geothermal heat keeps the deep settlements warm. Not tropical warm, not even room temperature warm by old Earth standards, but warm enough that water stays liquid, that humans can live without constant layers of insulation, that life continues. The ocean beneath its miles-thick shell of ice is still liquid, still cold, hovering just above freezing, throughout much of its volume, but liquid. Ice is an excellent insulator, and the thicker it gets, the better it insulates. It's created a stable environment below, a cold but protected world where the physics of liquid water still apply. And in that cold darkness, life persists. The hydrothermal vents are still active, still pouring out their mineral-rich superheated water, still supporting their strange ecosystems of tube worms and bacteria and blind shrimp. They've been doing this for 100 years now without the sun, and they'll keep doing it for millions more. They're the champions of Earth's biosphere, though they probably don't know it. They just keep living, keep metabolizing, keep being wonderfully, stubbornly alive in conditions that would kill almost anything else. And here's something remarkable. These vent ecosystems have actually diversified. With the surface ecosystems gone, there's less competition for resources in the deep ocean. Organic matter that used to be consumed in the upper water column now sinks to the depths. Nutrients are concentrating around the vents. Evolution, which never sleeps, has had 100 years to work with. New species are emerging, variations on the old themes, creatures even stranger than the ones that existed before, if that's possible. The deep ocean is having its moment, evolutionarily speaking. It's the Cambrian explosion in miniature, happening in slow motion in the crushing dark. On land, or what used to be land before it became a lifeless frozen waste, nothing survives. The surface is sterile, dead as the moon, as dead as Mars, as dead as any airless rock floating through space. But underground? Underground, humanity has built something unexpected. Cities, Real cities, not just survival settlements. Underground metropolises carved out of rock, spanning miles in their extent, housing thousands of people. They're lit by LED lights powered by geothermal plants. They're heated by wells drilled deep into the Earth's crust, tapping heat that's billions of years old. They're ventilated by systems that recycle air, scrub carbon dioxide, add oxygen from chemical processes. They're, in their own strange way, thriving. The largest of these cities is probably beneath what used to be Iceland. The island's position on the mid-Atlantic ridge means access to abundant geothermal energy, and 100 years of continuous excavation has created a vast network of chambers and tunnels. Reykjavik below, they call it, or just the deep in casual conversation. It houses perhaps 50,000 people, a significant fraction of Earth's remaining population. There are other cities, one beneath Yellowstone, built into the caldera of the supervolcano, dancing with danger, but kept warm by magma that's never far away. One in New Zealand, one in Japan, smaller settlements scattered around other geothermal sites. And then there are the deep mines that have been converted to habitations, old coal mines, old copper mines, dug deeper and deeper over the decades, following the warmth downward. The population of Earth after a century has stabilized at maybe 1 million people, perhaps a bit more. It's hard to maintain accurate census data when your entire species lives underground in scattered settlements, but estimates suggest something in that range, from 8 billion to 1 million in 100 years. It's a catastrophic decline, a genetic bottleneck of unprecedented severity. But 1 million is enough. Enough for genetic diversity, enough to maintain civilization, enough to continue the species. And life underground has developed its own culture, its own rhythms, its own strange beauty. Children are born who have never seen the sky, never seen a cloud, never felt rain, never experienced wind. These concepts are abstract to them, things from history books and old videos. They grow up in tunnels lit by electric lights that never change, never dim, never vary in color temperature. Day and night are arbitrary designations marked by shift changes at the geothermal plants, by sleep schedules that are largely a matter of personal preference. Education continues. Schools exist in underground chambers where children learn mathematics and physics and history. They learn about Earth's surface, though to them it's as alien as another planet. They learn about the sun, that mythical star their great-great-grandparents knew. They see pictures, old photographs from before, carefully preserved, of blue skies and green trees, and that bright yellow disk that gave light and warmth. Some believe the pictures are real. Some think they're exaggerated, that surely the sun couldn't have been that bright, that skies couldn't have been that blue. It's hard to believe in something you've never experienced. The elderly, the very few who remember, try to explain, try to capture what it was like to stand in sunlight. But how do you describe warmth from above? How do you explain the quality of natural light, the way it changes through the day, the particular orange glow of sunset? How do you convey the simple pleasure of lying in grass and watching clouds drift by? Language fails. Memory fails. The experience is too far removed from anything the young have ever known. So the sun becomes mythology, stories told to children. Once upon a time there was a star in the sky, and it gave light to the world, and everything grew and thrived beneath it. It has the cadence of a fairy tale. The children listen, rapt, imagining this impossible, beautiful thing. And then they go back to their lives in the eternal, unchanging underground, where the lights are always on and the temperature is always the same, and the sky is solid rock 100 meters above their heads. Food production has become sophisticated. Massive hydroponic farms occupy entire chambers, lit by precisely calibrated LED arrays that simulate the spectrum of sunlight, or at least the parts that plants need. Potatoes, soybeans, wheat, rice, tomatoes, lettuce. The same crops that sustained humanity in those first desperate years, now grown with a century of optimization and experience. Yields are good. Nobody's starving, which is more than could be said for those first terrible decades. Protein comes from aquaculture. Fish farms in underground pools filled with water pumped from deep aquifers. Tilapia mostly, some carp, a few other hardy species. And yes, insect farms. Crickets and mealworms grown in vast containers, harvested for their protein-rich bodies. People have gotten used to it. The younger generations don't even think it's strange. It's just food, processed into flour, mixed into breads and pastes, providing essential amino acids. Tastes fine, especially if you've never known anything else. Water is abundant, surprisingly. Ice from the surface is melted using waste heat from the power generation systems. It's clean, pure water. The cold has killed everything, and the ice that forms from seawater leaves the salt behind in a concentrated brine. So melted surface ice is actually fresh water, which is convenient. One less thing to worry about, and there are plenty of other things that require worry. The power grid is stable. Geothermal plants generate electricity constantly, reliably, without the weather-dependent variations that plagued the old surface world. Nuclear plants ran for the first few decades, but nuclear fuel runs out eventually, and after about 50 years, the last reactor was shut down. Everything is geothermal now. Heat from the Earth's core, channeled through wells, turned into steam, turned into electricity. It's renewable on any timescale that matters to humanity. The Earth's core will outlast our species by eons. Technology has advanced in some directions and stagnated in others. Computer technology continues to develop. There's not much to do in the underground tunnels, so entertainment and communication technology has flourished. Virtual reality is popular, let me tell you. When your physical reality is grey rock walls and artificial light, the appeal of a simulated environment is tremendous. People spend hours in VR, exploring simulated outdoor environments, walking through forests that don't exist anymore, standing on beaches that are buried under miles of ice. But transportation technology has simplified. No cars, where would you drive? No aircraft, there's no sky, just electric trains in tunnels, moving people and goods between settlements, walking mostly within the cities themselves. The world has gotten smaller, more compact, more efficient in some ways, more limited in others. Medicine has improved, oddly enough. With a smaller population and stable environment, epidemic diseases are less of a threat. The cold surface kills pathogens. The isolated settlements prevent spread between communities. Genetic diseases are tracked carefully. With such a small population, every genome matters. Prenatal screening is universal. It's a bit eugenics adjacent, which makes people uncomfortable. But when you're working with a species bottleneck this severe, you can't afford genetic disorders that might have been manageable in a population of billions. Mental health is perhaps the greatest challenge. Depression rates are high, which you'd expect in a species living in artificial caves lit by LEDs. Seasonal affective disorder is universal. It's always winter underground, metaphorically speaking. But there are treatments. Light therapy, though it's a bit ironic using artificial light to treat the effects of living by artificial light. Medications, counselling, and most importantly, community. People take care of each other. They have to. There's no one else out there. Your neighbours aren't just neighbours. They're the entirety of your available social world. So bonds are strong. Communities are tight-knit. People look out for each other because the alternative is unbearable isolation. Art has taken strange new directions. Visual art is mostly abstract now. How do you paint landscapes when you've never seen one, when the very concept of horizon is foreign? Music continues, though instruments have evolved. Fewer wind instruments, controlled breathing is important when air is recycled, more electronic compositions. Literature is popular. Stories about the old world, the sunlit world, written by people who have only the vaguest idea of what they're describing, creating something between historical fiction and fantasy. There's a genre of literature called surface fiction that's popular among young people. Stories set in the old world, full of wildly inaccurate descriptions of how weather worked or what plants looked like, written by authors who've never experienced either. The elderly find them amusing or painful, depending on their mood. The young find them inspiring. They're imagining a world they never knew and will never see, creating mythology from fragments of history. Scientific research continues. Understanding geothermal systems is critical. These are the life support systems for the species, so they're studied intensively. Deep drilling techniques improve. Methods for tapping heat from greater depths, from hotter rock, extending the available energy resources. There's research into closed-loop ecosystems, trying to achieve perfect recycling of resources. Nothing can be wasted when you're living in a sealed environment. And there's still astronomy, believe it or not. Telescopes can't be built on the surface anymore. The temperature would shatter any lens or mirror. But there are plans to drill vertical shafts up through the ice, creating viewing tubes to the sky above. The stars are still there after all, still visible, though now they're visible all the time since there's no daylight to wash them out. Earth may have lost its sun, but the universe hasn't gone anywhere. Some scientists are tracking Earth's trajectory through space. We've travelled about 587 billion miles in the past century. That's roughly 0.01 light years. We've barely left the neighbourhood, cosmically speaking. The solar system is far behind us, but the next star system is still unimaginably far ahead. We're in the vast empty space between stars, and we'll be here for thousands of centuries at least. But people track the journey anyway. Mark the distance travelled. Calculate where we're headed, even though where we're headed is nowhere in particular at any time scale that matters. The moon is still with us, of course, still orbiting, still creating tides in the ocean beneath the ice, though those tides are muted now by the friction of all that frozen water. The moon is dark, just a black circle blocking stars, but its gravitational presence is comforting somehow. We're not completely alone on this journey. We have our companion, our satellite, our faithful moon that's been with Earth for 4.5 billion years and shows no sign of leaving. So this is Earth after a century without the sun, a frozen ball of ice and rock hurtling through interstellar space at 67,000 miles per hour. Surface temperature, minus 400 degrees Fahrenheit. Atmosphere, beginning to freeze. Oceans, locked under miles of ice. Surface life, extinct. But deep inside, in carved caverns warmed by ancient heat, humanity survives. 1 million strong. Changed, certainly. Adapted to a lifestyle that would have seemed like science fiction or nightmare to their ancestors. But alive, still thinking, still learning, still creating art and raising children and telling stories. Still human in all the ways that matter. The first 100 years are the hardest, they say, though that's probably just something people tell themselves to stay optimistic. The truth is, every year is hard when you're living in a way humans were never meant to live. But hard doesn't mean impossible, and humanity has proven over this century that we can adapt to almost anything. We lost the sun. We lost the surface world. We lost the vast majority of our species, but we didn't lose everything. We kept our curiosity, our creativity, our determination to continue, our stubborn refusal to simply give up and die. 100 years in the dark, and we're still here, still surviving, still hoping, against all reasonable expectation, that there's a future worth building. Maybe that's enough. Maybe that's all you can ask for when your star has abandoned you and you're left alone in the cosmic night. We endure, we adapt, we survive, and we keep the lights on down here in the deep places so that no one ever has to face the darkness alone. Let's step back for a moment, way back. Let's zoom out from the underground cities and the hydroponic farms and the people living in carved rock and look at Earth from a distance, from very far away, from the perspective of, say, an alien astronomer with a really good telescope watching our planet on its strange journey through the galaxy. What would they see? A rogue planet, a wanderer, a world that somehow escaped its star and is now travelling alone through interstellar space, following a path determined by nothing but inertia and the subtle gravitational influences of distant stars. Earth has joined a category of objects that astronomers have theorized about, but rarely observed. Planets without suns drifting between star systems, dark and cold, and utterly alone. And here's the thing about interstellar space. It's empty, profoundly, almost incomprehensibly empty. The distances between stars are so vast that even travelling at Earth's speed, 67,000 miles per hour, which sounds impressive until you think about it in cosmic terms, it would take tens of thousands of years to reach even the nearest star. And we're not heading toward the nearest star anyway. We're heading, well, off in some random direction determined by where Earth happened to be in its orbit when the sun disappeared. Space, it turns out, is very good at being spacious. So let's talk about what happens to Earth over very long timescales. Thousands of years, millions of years, the kinds of time frames that make human civilization seem like a brief flicker, that put our entire species' existence into a perspective that's simultaneously humbling and oddly comforting. Because if we're being honest, whether humanity survives or not, Earth itself will continue. The planet doesn't care whether it has a sun or not. It just keeps existing, keeps moving, keeps being a planet. Over the next 1,000 years, the surface temperature drops a bit more, settling somewhere around minus 450 degrees Fahrenheit. That's minus 268 degrees Celsius. That's cold enough that nitrogen, the most abundant gas in Earth's original atmosphere, starts to freeze. Not everywhere, not all at once, but in the coldest spots in the deep polar winters, which are now all the time. Nitrogen snow begins to fall. The atmosphere continues its slow collapse, settling onto the ground molecule by molecule, century by century. Eventually, and we're talking thousands of years here, Earth's atmosphere will be almost entirely solid, a frozen coating on an already frozen surface. The air itself will have precipitated out, leaving perhaps only a thin wisp of the lightest gases, hydrogen, helium, things that can't freeze even at these temperatures. Earth will look from the outside like a ball of ice and rock with no atmosphere at all. A dead world, indistinguishable from an asteroid except larger. But inside, deep inside, life continues. Humanity, or whatever humanity has become after thousands of years underground, still exists. The geothermal heat doesn't care about surface temperature. The core of the Earth remains hot, about 10,800 degrees Fahrenheit, unchanged by the loss of the sun. That heat bleeds upward slowly, constantly warming the deep places, and in those warm depths civilization persists. It's worth thinking about what that civilization might look like after 10,000 years, after 100,000 years. Humans are remarkably adaptable, but we also evolve, and evolution works faster in small populations under strong selective pressure, which is exactly what we have here. The descendants of the survivors will be adapted to underground life in ways we can barely imagine. Their eyes might change. When you live in artificial light that never varies, in an environment with no horizons and no distance greater than a tunnel's length, your eyes don't need to work the same way. Vision might become more sensitive to dim light, or less sensitive overall with other senses compensating. Hearing, touch, spatial awareness. These might become more important than sight in a world of stone corridors. Skin color will definitely change. Melanin, the pigment that protects against UV radiation from the sun, isn't needed underground. Over thousands of generations, you'd expect populations to become very pale, almost translucent, as the genes for melanin production are no longer selected for. We'd become, quite literally, creatures of the dark, adapted to a sunless existence in the same way that cave fish lose their pigmentation and eyes over evolutionary time. Size might change too. Smaller bodies require less energy, less food. In an environment where every calorie must be produced artificially, where resources are limited, there's selective pressure towards smaller body size. Not drastically smaller. We're not talking about shrinking to hobbit proportions in a few thousand years, but a gradual reduction in average height and mass. More efficient humans for a more constrained world. Psychology would shift in ways harder to predict. What does it mean for the human psyche when you never see the sky, when the farthest you can see is the end of a tunnel, when your entire universe is walls and ceilings and the same recycled air? We're social creatures, tribal creatures, but we're also creatures that evolved in open spaces, on savannas and coastlines and forests. Take away the openness, and something changes. Maybe we become more comfortable with enclosed spaces. Maybe agoraphobia becomes the norm and claustrophobia becomes rare. Maybe our sense of wonder shifts from the external to the internal, from exploring physical space to exploring ideas, art, mathematics, the infinite landscapes of imagination. Or maybe we stay essentially the same, psychologically. Humans are stubborn that way. We adapt to our circumstances, but we also carry our ancestral programming. People born in cities still feel drawn to nature. People who've never seen the ocean still find videos of waves soothing. Maybe deep down, 10,000 years from now, humans will still dream of sunlight and open skies, even if no one alive has experienced either. The cities would grow over these millennia, constantly excavating, expanding, following the warmth downward and outward, kilometers of tunnels, vast underground caverns that take hours to walk across, whole districts dedicated to different functions, agricultural zones, residential areas, manufacturing centers, research laboratories. A three-dimensional city sprawling through solid rock, limited only by the available geothermal energy to power it, and the cities would connect eventually. Tunnels stretching hundreds of miles between settlements, underground highways linking the scattered enclaves of humanity. Travel between cities would become possible, even routine. The underground would become a network, a web of human presence spreading through the Earth's crust. Not on the surface is dead, uninhabitable, forgotten, but below, always below, in the warm embrace of the planet's interior heat. Technology would advance in odd directions. You wouldn't have aeronautics. There's no air to fly through. You wouldn't have maritime engineering. The oceans are frozen solid and unreachable beneath miles of ice. But you'd have incredible tunneling technology. advanced drilling, sophisticated mapping of geothermal resources, methods for tapping heat from greater and greater depths. Your engineers would be experts in things like rock mechanics and thermal transfer and closed-loop life support systems. Computing would likely advance dramatically. When your entire world is artificial and controlled, computation becomes even more central to existence. Managing air recycling, water distribution, power generation, food production, it all requires sophisticated systems, and with limited physical space for expansion, you grow inward. Virtual spaces, simulated environments, digital worlds that exist only in computer memory but feel as real as stone corridors because, let's be honest, you've never experienced anything else to compare them to. Art would be strange. Music composed in perfect acoustic chambers carved specifically for sound. Visual art that's never seen natural light, created under the flat spectrum of LEDs. Literature about worlds the authors have never seen and can barely imagine. There might be an entire artistic tradition based on darkness, on absence, on the negative space where the sun used to be. Elegies for lost things, meditations on memory and forgetting. What does your culture look like when your founding myth is catastrophic loss? And religion. Oh, there would definitely be religions. Probably many of them. Some would worship the sun, the lost star, the golden god that abandoned humanity. Sacred texts preserving memories of sunlight, rituals celebrating the dawn that never comes, prayers for the return of warmth from above. Other religions might reject the sun, might frame the underground existence as a kind of return to the womb, a spiritual descent into enlightenment, the earth as mother, providing for her children, protecting them in her warm depths. There might be schisms about whether the sun was real at all. Think about it. 10,000 years from now, 50,000 years from now, with only ancient records and dubious stories to prove it existed. Some would believe. Some would say it's myth, metaphor, a teaching story about human hubris or divine judgment or some other moral lesson. The old videos and photographs would be examined like religious scholars examining scripture, some accepting them as truth, others claiming they're artistic interpretations or allegories or outright fabrications. History would be complicated. How do you maintain accurate history over 10,000 years in a closed society? Stories drift. Facts become legends, legends become myths. Eventually, the truth of what happened, that the sun disappeared inexplicably one Tuesday afternoon, might be so buried under layers of interpretation and reinterpretation that nobody really knows what actually occurred. Just that once, long ago, something changed. The world ended and began again, and here we are, living in the age that followed. Over hundreds of thousands of years, even millions of years, the Earth continues its journey through space. We're traveling through the galaxy, which is itself rotating, which means we're following a complex spiraling path through three-dimensional space. Sometimes we might pass relatively close to other stars. Close, meaning within a few light years, which is still unimaginably far. Close enough that those stars become bright points in the sky visible from the surface, if anyone were on the surface to see them, which they're not. Could we ever encounter another star closely enough for it to matter? Closely enough that its light and heat could reach Earth, could potentially warm the surface, could give us a second chance at a sunlit existence. The odds are not good. Space is really remarkably empty. The probability of a rogue planet passing close enough to a star to be captured by its gravity, or even just to pass through the habitable zone temporarily, is extremely low. You'd need to get within about 1 astronomical unit, 93 million miles, the distance Earth used to orbit from our Sun, for the star's heat to matter. And stars, even though there are hundreds of billions of them in the galaxy, are so far apart that most of space is nowhere near any star. If we did pass near a star, it would take centuries to approach, centuries in the habitable zone if we passed through it, then centuries departing. It would be this gradual warming, the ice beginning to melt, the atmosphere sublimating back into gas, the surface slowly, impossibly coming back to life. Can you imagine? Generations would pass during the approach. People would live their entire lives watching the new star grow brighter in the sky, knowing they wouldn't live to see the full warmth, but their children might, their grandchildren certainly. And then what? Would humanity return to the surface? Would we remember how to live under a sky? Would we want to after so many thousands of years underground? Or would we stay below in our familiar tunnels, acknowledging the star but not depending on it, having learned our lesson about the reliability of suns? But this is all speculation on top of speculation. The far more likely scenario is that Earth just continues, alone, drifting through the dark spaces between stars for millions of years, billions of years, until eventually the galaxy itself changes shape, until the universe continues its expansion and even the stars grow further apart. The geothermal heat will last for billions of years, long enough that it's effectively infinite from humanity's perspective. The Earth's core will cool, eventually. Physics demands it, but so slowly that civilizations will rise and fall thousands of times before it makes a measurable difference. Our descendants, if they survive, if they continue, could live underground for longer than our species has existed on the surface, could outlast not just human civilization, but the human species itself, evolving into something new, something adapted to eternal darkness, something that's forgotten the sun so completely that they don't even have a word for it anymore. This is the long dark, the deep future. Earth as a rogue planet carrying its cargo of stubborn life, wandering alone through a galaxy full of light but surrounded by darkness. It's melancholy, perhaps. Lonely, certainly. But there's something almost peaceful about it, too. We're no longer dependent on the whims of a star. We're self-sufficient, drawing on our own resources, our own heat, our own determination. We've become, in a strange way, independent, free, cut loose from the solar system that birthed us, following our own path, making our own fate. It's not the story we would have chosen. Given the choice, we'd take the sun back in a heartbeat, but it's the story we have, and we're making the most of it, surviving, adapting, continuing. Earth spins through the void, a tiny world in an incomprehensibly large universe, carrying something precious and rare: life, consciousness, the ability to wonder and question and imagine. The universe may be vast and cold and indifferent, but here, on this small frozen world hurtling through the dark, something warm persists. The long dark continues, miles of ice above, miles of rock below, and in between, in the warm middle places, life finds a way. Not the life that was, not the sunlit world of forests and oceans and blue skies, but life nonetheless, different life, adapted life, stubborn, persistent, unwilling to quit life. We're still here, against all odds, despite impossible circumstances, in defiance of entropy and common sense, and the vast indifference of the cosmos. We're still here, and that has to mean something. Now, let's come back to reality for a moment, or rather, let's acknowledge what reality actually is, because we've been living in a thought experiment for quite a while now, and it's worth remembering that none of this can actually happen. The sun isn't going to disappear. It can't disappear. The laws of physics simply don't allow for it. Stars don't vanish. They're not light bulbs that can be switched off. They're massive balls of hydrogen undergoing nuclear fusion, and they follow very specific, very predictable life cycles. Our Sun is a main sequence star, about halfway through its life, and we know exactly what its future holds. Not because we're guessing, but because we've observed thousands of other stars at various stages of their lives, and we understand the physics well enough to predict what happens next. So what does actually happen to the Sun? What's the real end of our star, the one we'll actually experience if humanity is still around in 5 billion years? The Sun will die, but it will die slowly, gradually, and with plenty of warning. So much warning that if we're still around, we'll have millions of years to prepare. Possibly hundreds of millions of years, depending on when we decide the situation has become untenable. Here's how it works. The Sun is currently in what's called the main sequence phase of stellar evolution. It's been fusing hydrogen into helium in its core for about 4.6 billion years, and it will continue doing so for another 5 billion years or so. This is the stable phase, the phase where the Sun is reliable and consistent and basically the perfect star for supporting life. We lucked out, cosmically speaking. But eventually the hydrogen in the core runs out. Not all at once, there's still plenty of hydrogen in the outer layers, but the core gets depleted. And when that happens, fusion stops. Without fusion producing outward pressure, the core starts to collapse under its own gravity. And when gas compresses, it heats up. The core gets hotter and denser, hot enough that hydrogen fusion starts happening in a shell around the core, instead of in the core itself. This shell fusion produces more energy than core fusion did, a lot more energy, and that energy pushes the outer layers of the Sun outward. The Sun swells, expands, becomes what astronomers call a red giant. And by giant, we mean really dramatically large. The Sun will expand until its outer edge reaches somewhere around Earth's current orbit. Maybe a bit closer, maybe a bit farther. The models aren't perfectly precise, but basically to where we are now. Now, before you panic about being swallowed by an expanding Sun, remember that this process takes millions of years. It's not like the Sun inflates like a balloon over a weekend. It grows slowly, incrementally, getting larger and larger over timescales that make human civilization look like a brief moment. We'd see it coming. We'd have time to do something about it. Also, and this is somewhat comforting, Earth's orbit will probably expand too. As the Sun loses mass, and it will, shedding its outer layers into space as it becomes a red giant, its gravitational pull weakens slightly. The planets, no longer held as tightly, drift outward. Earth might end up in a wider orbit, just far enough out to avoid being engulfed, or it might not. The calculations are tricky, and there's genuine uncertainty about whether Earth gets swallowed or merely roasted. But either way, the surface becomes uninhabitable long before the Sun actually reaches us. As the Sun brightens and swells, temperatures on Earth rise. The oceans evaporate, the atmosphere thickens with water vapor, creating a runaway greenhouse effect like what Venus has now. Within a few 100 million years, maybe 1 billion at most, Earth's surface will be too hot for liquid water to exist. And without liquid water, life as we know it becomes impossible. So the realistic scenario isn't sudden catastrophe, it's gradual decline, a slow warming over millions of years, giving any sufficiently advanced civilization plenty of time to notice and respond. Which brings us to an interesting question. What would we do? The obvious answer is leave. If Earth is becoming uninhabitable, you find somewhere else to live. Mars, maybe, though Mars has its own problems, and by the time Earth is getting too hot, Mars might also be warming up. Different planets, different distances, it's complicated. The moons of Jupiter or Saturn look more promising. Europa, Ganymede, Titan. They're frozen now, but as the sun expands and brightens, they'll warm up. The habitable zone of the solar system will move outward, and what's currently too cold will become just right. We'd have to terraform, or at least build habitats, but we'd have millions of years to figure it out. That's not a technology problem at that time scale. That's a planning problem. Where do we want to go? How do we move billions of people? What infrastructure do we need? These are solvable questions when you have geological ages to work with. Or, and this is where it gets interesting, we could do what we imagined in our thought experiment. We could go underground. We could abandon the surface to the heat and solar radiation, and we could build our civilization deep in Earth's crust, powered by geothermal energy. Because here's the thing, geothermal energy doesn't depend on the sun. It works whether the sun is dying, dead, or perfectly fine. The heat from Earth's core will be available for billions of years, regardless of what's happening in the sky above. If we knew the sun was dying, and we would know we'd see it happening, we could prepare. We could build the underground infrastructure while the surface was still habitable. Massive tunnel systems, geothermal plants, hydroponic farms, air recycling systems. Everything we talked about in our thought experiment, but built gradually, carefully, with all the resources of surface civilization available to help. And then, when the surface finally became too hot, when the oceans boiled away and the atmosphere became a toxic steam bath, humanity would just move downstairs, close the doors, seal the airlocks, continue civilization in the cool, stable depths where temperature doesn't depend on the sky. We'd survive the sun's death, not by leaving Earth, but by going deeper into it, by making Earth itself our spaceship, our life support system, our home regardless of what the universe throws at us. This is actually a more realistic survival strategy than you might think. Moving billions of people to other planets is hard. Really hard. The logistics are nightmarish. But moving billions of people underground, that's just construction. Difficult construction, yes, engineering on an enormous scale. But fundamentally it's just digging and building and installing systems. We know how to do these things. We've been digging tunnels and mining and building underground for thousands of years. We'd just be doing it much more extensively, much more systematically, with the goal of making it permanent. You'd save incredible amounts of energy too. On the surface, you need heating, cooling, protection from radiation, structural strength to withstand weather. Underground, the temperature is stable. There's no weather. The radiation shielding is provided by miles of rock. You just need lights, air recycling, and food production. Much simpler in some ways. There's even a name for this concept in scientific literature, a subsurface civilization. Not science fiction, but actual research into how a civilization might survive after its star becomes uninhabitable. The papers are fascinating. They work through the engineering, the energy requirements, the challenges of closed-loop life support, and the conclusion is generally, yes, this could work. Not easily, not comfortably perhaps, but survivably. So the realistic scenario is this. 5 billion years from now, give or take, the sun starts to die. We see it coming. We have millions of years of warning. We either leave Earth for cooler locations in the outer solar system, or we retreat underground and live off Earth's own internal heat. Either way, we survive. Changed, certainly. Living very differently than we do now, but alive, continuing, adapting to new circumstances the way life always does. And here's something worth considering. Would that underground civilization look much different from the one we imagined in our thought experiment? Whether the sun disappeared suddenly or died gradually, whether we had warning or not, the solution is the same. go underground, use geothermal energy, grow food under artificial lights, recycle everything. The engineering is identical, the lifestyle is identical. The only difference is whether we built it in panic over a few years or carefully over a few million years. So in a strange way, our thought experiment about the sun disappearing is actually useful preparation for the real scenario of the sun dying. The challenges are the same, the solutions are the same. We're just compressing the timeline for dramatic effect, speeding up what will actually be a very slow, very manageable transition. There's something almost reassuring about that, isn't it? This impossible scenario we've been exploring, it's not completely divorced from reality. It's an extreme version of a real problem we'll actually face. And if we can imagine surviving the impossible version, the sudden catastrophe with no warning, then surely we can survive the real version with millions of years to prepare. We're good at preparation, humans. We're good at planning. We're good at engineering solutions to problems. Give us enough time and enough motivation and we can figure out almost anything, moving underground to survive the death of our star. That's just another engineering challenge. A big one, certainly. Maybe the biggest one, but not impossible. Not even close to impossible. And who knows? Maybe by the time the sun actually starts to die, we'll have other options we haven't even thought of yet. Maybe we'll have mastered interstellar travel and colonized other star systems, so losing the sun is sad, but not catastrophic. Maybe we'll have figured out how to move planets, to push Earth outward to a safer orbit as the sun expands. Maybe we'll have technology that seems like magic to us now, that makes the whole problem trivial. Or maybe we won't. Maybe we'll still be roughly where we are now, technologically speaking, just with better versions of current technology. Better tunneling equipment, better fusion reactors. We'll definitely have fusion figured out by then, surely. Better hydroponics, better recycling systems, and that's fine too. That's enough. We don't need miracle technology. We just need competent engineering and the will to survive. Because that's the real lesson here, isn't it? The sun can be lost, either suddenly in a thought experiment or gradually in reality, and humanity can survive. Not unchanged, change is inevitable, but alive, still thinking, still creating, still being human in all the ways that matter, even if we're doing it in conditions our ancestors would find unimaginable. We're adaptable. That's our superpower as a species. Not strength, not speed, not venom or armor or any of the advantages other animals have. Just adaptability. The ability to look at impossible circumstances and say, okay, this is terrible, but here's how we survive anyway. The ability to find solutions, to imagine alternatives, to refuse to give up even when giving up would be the logical thing to do. The sun disappearing is impossible, but even if it were possible, we'd figure it out. We'd survive. We'd build something new from the ruins of what was lost. We'd keep going, because that's what humans do. And the sun dying slowly over millions of years, that's not just possible, it's guaranteed. It's going to happen. And we'll handle it. We'll see it coming. We'll prepare, and we'll adapt. We'll build underground if we need to. We'll move to other planets if that's better. We'll do whatever it takes. Because we're survivors, we're problem solvers. We're the species that looked at the challenge of crossing oceans and built boats, that looked at the challenge of flight and built airplanes, that looked at the challenge of space and built rockets, that looked at the challenge of computation and built computers. We see problems and we solve them. That's what we do. Losing the sun, whether suddenly or slowly, is just another problem. A really big problem, admittedly. Maybe the biggest problem, but still just a problem. And problems have solutions. We'll find ours, we always do. So rest easy. The sun isn't going anywhere for 5 billion years. And when it does start to die, we'll be ready. We'll have a plan. We'll have options. We'll have the technology and the knowledge and the determination to survive. The universe may be vast and indifferent and full of dangers, but it's also full of opportunities. And humanity, stubborn and adaptable and impossibly determined, will find those opportunities. We'll make our own light. We'll generate our own warmth. We'll survive on our own terms. The sun can die. The universe can change. The circumstances can become impossible. But we'll still be here. Still thinking. Still dreaming. Still reaching for the future, whatever that future looks like. That's not faith. That's not optimism. That's just history. That's what humans have always done, and what we'll keep doing for as long as we exist. The sun will die, but we'll survive it. Count on it. So we've journeyed through this impossible scenario together. We've watched the sun vanish. We've tracked the temperature plummeting. We've followed humanity underground. We've seen Earth become a rogue planet, wandering alone through the galaxy for millions of years. We've explored both the catastrophic and the survivable, the immediate and the deep future, the physics and the human response. Now let's step back and ask, what was the point of all this? Why spend time imagining something that can't happen? What does this thought experiment actually teach us? The answer, I think, is gratitude. Deep, profound, often overlooked gratitude for the sun. We take the sun for granted. Of course we do. It's always there. Every morning, reliable as clockwork, it rises. Every day it provides light and warmth. Every season it marks the passage of time. It's been doing this for our entire lives, for our parents' lives, for our ancestors' lives, stretching back through every generation of humans who have ever existed. The sun is the ultimate constant, the one thing you can count on, day after day, year after year, millennium after millennium. Except now, having imagined its absence, we understand what that constancy means. We understand what the sun actually does for us. Not just provides light and heat in some abstract sense, but specifically, precisely, continuously makes our existence possible. Every breath you take, the oxygen in the air comes from plants, and plants need sunlight to produce oxygen through photosynthesis. Every meal you eat, the food comes from plants, or from animals that eat plants, and plants need sunlight to grow. Every comfortable temperature, the warmth of your home, the pleasant climate of your region exists because the sun heats the Earth's surface and drives weather patterns. Every drop of rain, the water cycle depends on solar heating to evaporate water from the oceans and carry it inland. The sun isn't just important, it's fundamental. It's the engine that drives basically everything about Earth's surface environment, and we barely think about it. We complain when it's too sunny, when it's too hot, when we get sunburned. We look forward to cloudy days, to shade, to air conditioning. We treat the sun like it's sometimes an inconvenience, something to be managed or escaped from. But spend a few hours imagining its absence, and suddenly you see it differently. Suddenly you notice what an incredible gift it is. This massive ball of nuclear fire, 93 million miles away, close enough to warm us, but far enough not to incinerate us, faithfully fusing hydrogen into helium, producing exactly the right spectrum of light for life to thrive, maintaining a stable output for billions of years. The Goldilocks conditions aren't just about Earth's distance from the sun. They're about the sun itself being exactly the right kind of star. If the sun were bigger, it would burn hotter and die faster. If it were smaller, it would be cooler and the habitable zone would be closer in. If it were more variable, life would struggle with the temperature swings. But it's not. It's a main sequence G-type star, stable and medium-sized and perfectly suited for supporting a living world. And it's ours. We won the cosmic lottery, and most of the time we don't even buy a ticket. This thought experiment teaches us to appreciate what we have, to notice the sun, to acknowledge, at least occasionally, that every moment of our existence depends on this star that we usually ignore. Tomorrow morning, when you see sunlight streaming through a window, maybe you'll pause for just a second. Maybe you'll think, that's light that's travelled 8 minutes and 20 seconds from the surface of the sun. That's fusion energy converted to photons, crossing the void of space, arriving here to warm my face. Maybe you'll feel a moment of gratitude for something so fundamental we usually forget it's there. The second lesson is about Earth's resilience, and this one might surprise you, given how much of our scenario was catastrophic. But think about it. Even without the sun, Earth itself continues. The planet keeps spinning. The core stays hot. Geothermal energy remains available. Life, at least some life, survives. The deep ocean ecosystems around hydrothermal vents don't even notice the sun is gone. They just keep living, keep thriving, keep being proof that life doesn't always need sunlight. This is remarkable. It means Earth has backup systems. The sun is the primary source of energy for surface life, yes, but it's not the only source of energy on the planet. The Earth's own internal heat, generated by radioactive decay and left over from the planet's formation, provides an alternative. Not as abundant as solar energy, not as accessible, but available, permanent, reliable on billion-year timescales. Those chemosynthetic bacteria at the hydrothermal vents, they evolved long before photosynthesis. They might be the oldest form of life on Earth, and they survived mass extinctions, ice ages, asteroid impacts, every catastrophe that's hit this planet over 4 billion years. They don't need the sun. They never did. They're Earth's insurance policy, the proof that life can persist under the worst possible conditions. And that's somewhat comforting, isn't it? If humans disappeared tomorrow, and in the grand scheme of things we probably will eventually, Earth would be fine. Life would continue. Maybe not the life we know, maybe not the charismatic megafauna and beautiful forests, but life. Microbial life, deep-dwelling life, patient and stubborn, and impossible to kill. The planet doesn't need us. It doesn't need any particular form of life. It's a stage where life performs, but the stage remains whether the performers survive or not. That might sound depressing, but I find it oddly hopeful. It means Earth is robust, resilient, capable of supporting life even under absurd conditions. It means our planet has depths we don't usually appreciate, resources we don't usually access, potential we don't usually consider. The third lesson is about human adaptability, and this one's complicated because our scenario required us to imagine both tremendous suffering and remarkable resilience. Humans are fragile in some ways. We need narrow temperature ranges, specific atmospheric conditions, regular supplies of food and water. Take away the sun, and the vast majority of humanity dies. There's no getting around that grim reality. We're solar-dependent creatures living on a solar-powered planet, and removing the power source is catastrophic. But, and this is important, we're not entirely dependent. We have technology, we have intelligence, we have the ability to create artificial environments, to grow food without sunlight, to generate heat without solar input. We're not just passively dependent on natural conditions like most species. We can engineer alternatives. In our thought experiment, a remnant of humanity survived underground, living off geothermal energy, creating an entirely artificial ecosystem. That's not science fiction. That's extrapolated engineering. We have the basic technology right now. Geothermal power plants exist. Hydroponics exists. Underground construction exists. We'd just be doing it more extensively, more desperately, under worse conditions. But the fundamental knowledge is already there. This means humans are more adaptable than we might assume. We're not just smart apes who happen to evolve on a nice planet. We're tool-using, problem-solving, environment-modifying apes who can potentially survive in conditions far outside what our biology evolved for. We're not adapted to underground life, but we could adapt to it. We're not designed for artificial environments, but we could build them and live in them. There's a philosophical question here about whether that's a good thing, whether our ability to technologically overcome natural limitations is a form of transcendence, or just a way of postponing inevitable extinction. But setting aside the philosophy, it's simply a fact. Humans can survive in a wider range of conditions than our biology would suggest. We extend our survival range through intelligence and technology. That's our evolutionary niche, being the species that can live almost anywhere if we're clever enough about it. The fourth lesson is about perspective, about understanding our place in the universe, about recognizing both how important we are and how ultimately insignificant. In our scenario, losing the sun is humanity's ultimate catastrophe. It's the end of the world as we know it, the collapse of civilization, the death of billions. From our perspective, it's the worst thing imaginable. The apocalypse, the extinction event to end all extinction events. But from the universe's perspective, the sun disappearing wouldn't even be noticeable. The galaxy contains 200 billion stars. If one vanished, impossibly inexplicably, the galaxy wouldn't change. Other stars would continue fusing hydrogen. Other planets would continue orbiting. Life on other worlds, if it exists, would be completely unaffected. The universe would proceed exactly as before, entirely indifferent to our local catastrophe. This is humbling. We live in a universe that doesn't care whether we survive or not. The cosmos has no opinion on human existence. We're not the center of creation, not the point of the universe's existence, not particularly special from the perspective of physics or astronomy. We're just one species on one planet, orbiting one unremarkable star in one ordinary galaxy, among hundreds of billions. And yet, and this is the paradox, we matter enormously. Maybe not to the universe, but to ourselves. Our experiences, our consciousness, our ability to understand and appreciate and create, these things have value even if that value is local, subjective, temporary. The universe might not care whether we survive, but we care. And that caring, that determination to continue existing, that stubborn insistence that we matter, even if the cosmos disagrees, that's beautiful in its own way. We're cosmically insignificant, but locally precious. Both things are true simultaneously. And holding both perspectives at once, the vast indifference of the universe and the intimate importance of human experience, that's what it means to understand our place in things. The fifth lesson, maybe the most important one, is about impermanence, about accepting that everything ends, even things that seem eternal. The sun feels permanent. It's been there every day of your life. It was there for your parents' lives, your grandparents' lives, every human who's ever lived. It's been there for 4.5 billion years. It will be there for 5 billion more. On human timescales, it might as well be eternal. But it's not. The sun will die. Not soon, not in any time frame that matters to us or our civilization, but eventually, inevitably. The universe doesn't allow for permanent stars any more than it allows for permanent civilizations or permanent species or permanent anything. Everything that exists will eventually cease to exist. That's not pessimism, that's thermodynamics. And somehow that's okay, because impermanence doesn't mean meaningless. The sun's eventual death doesn't make its current life less valuable. Its warmth and light matter right now, regardless of what happens in 5 billion years. Similarly, human life matters now. Human civilization matters now. Human experience and love and art and discovery matter now, even though none of it will last forever. This thought experiment, imagining the sun's disappearance, is practice for accepting impermanence. Practice for acknowledging that the things we depend on won't always be there. Practice for appreciating what we have while we have it, because the alternative is taking everything for granted until it's gone. Maybe that's the real point of all this, not to scare ourselves about cosmic catastrophes, not to calculate survival probabilities or design underground cities, but simply to notice what we usually ignore, to appreciate what we usually take for granted, to recognize that this moment, right now, with the sun faithfully shining and Earth's surface comfortably habitable and life thriving in conditions that are actually quite narrow and quite special, this moment is a gift. An impermanent gift, certainly, a temporary gift on cosmic timescales, but a gift nonetheless. So maybe tomorrow, when you step outside, you'll look up at the sun. Not directly, never directly, please don't burn your retinas, but acknowledge it. Thank it if you're inclined toward that sort of thing, or just notice it. Recognize what it does for you. Appreciate the 8-minute-old light warming your face. Feel gratitude for the most important thing in your world that you almost never think about. Because the sun isn't going anywhere, not tomorrow, not for billions of years, but we've spent all this time imagining what would happen if it did. And now, coming back to reality, maybe we see it a little differently. Maybe we appreciate it a little more. Maybe we understand, in a way we didn't before, just how lucky we are to have a star. Our star, faithful and constant and absolutely essential. Still there, still shining, still making everything possible, and worth being grateful for. We've talked a lot about survival in abstract terms. Humanity going underground, living off geothermal energy, adapting to life without sunlight. But let's get specific now. Let's talk about the actual science and engineering that would make survival possible, because the difference between a thought experiment and reality is details, and the details, as it turns out, are fascinating. Let's start with the most fundamental question. Where does the heat come from? We've mentioned geothermal energy repeatedly, but what is it really? Where does Earth's internal heat originate, and why does it last so long? The answer is actually twofold. Earth has two main sources of internal heat, and both are quite literally older than the Sun. Well, older than the Sun's current incarnation. The atoms themselves came from earlier stars, but you know what I mean. The first source is primordial heat, leftover warmth from Earth's formation 4.5 billion years ago. When the planet was forming, countless smaller objects, planetesimals they're called, crashed together, combining their mass. Every collision released kinetic energy as heat. Lots of collisions, lots of heat. So much heat that early Earth was partially molten, a ball of magma with a thin crust that kept breaking and reforming. That heat is still here. Not all of it. Earth has been cooling slowly for billions of years, but a substantial amount. The core of the Earth is still about 10,800 degrees Fahrenheit, roughly the same temperature as the surface of the Sun. That's primordial heat, stored in the planet's interior, radiating outward incredibly slowly because rock is an excellent insulator. The second source is radioactive decay. Deep in Earth's mantle, there are radioactive isotopes, mostly uranium, thorium, and potassium, that are slowly, continuously decaying. Radioactive decay releases heat. Not much heat per atom, but there are a lot of atoms in the Earth's mantle. Collectively, they generate about 20 terawatts of power. That's roughly twice the total power consumption of human civilization. Just sitting there, being radioactive, heating the planet from the inside. These isotopes have long half-lives, billions of years, which means they'll keep generating heat for billions of years more. Uranium-238 has a half-life of 4.5 billion years. Thorium-232 has a half-life of 14 billion years, which is longer than the current age of the universe. These aren't going to run out anytime soon. Put those two sources together, primordial heat and radioactive decay, and you have a planet that generates its own warmth, independent of any external star. Earth is, in a sense, its own heating system. Not as powerful as the Sun, obviously. The Sun provides about 174,000 terawatts to Earth's surface. Geothermal energy is only about 47 terawatts total, which is tiny by comparison, but 47 terawatts is still substantial. It's enough to support a civilization if that civilization is willing to live underground where the heat is concentrated. So how do you actually access that heat? How do you turn the Earth's core is hot into usable energy? The answer is geothermal wells. You drill down into the Earth's crust, deep enough that the rock is hot, and you pump water down. The hot rock heats the water, turning it into steam, and you pipe the steam back up. That steam can turn turbines, generating electricity, and then you condense it back into water and send it down again. It's a closed loop. You're essentially using the Earth as a giant heat exchanger. The key is getting deep enough. Temperature increases with depth at a rate called the geothermal gradient, roughly 25 degrees Celsius per kilometre on average. So at 1 kilometre deep, the rock is about 25 degrees Celsius warmer than the surface. At 2 kilometres, 50 degrees Celsius warmer. At 3 kilometres, 75 degrees Celsius warmer. You need to get to around 150 to 200 degrees Celsius to efficiently generate steam for power generation, which means drilling 3 to 4 kilometres deep in most places. That's deep, deeper than most mining operations, but it's not impossibly deep. We've drilled deeper than that for research and oil extraction. The technology exists. It's just expensive and technically challenging. But in a survival situation where geothermal energy is the difference between life and death, those challenges become very solvable very quickly. Some locations are easier than others. Iceland, sitting on a divergent tectonic boundary where two plates are pulling apart, has magma close to the surface. You don't need to drill as deep. Hot water is sometimes just a few hundred meters down. Other locations, like Yellowstone, sitting on a volcanic hotspot, or New Zealand with its active volcanism, also have accessible geothermal resources. But even places without obvious volcanism have geothermal potential. You just need to drill deeper, and in our scenario, with the surface uninhabitable and underground the only option, drilling deep becomes worth the effort. Now let's talk about food, because living underground is one thing, but living underground without starving is considerably better. Without sunlight, traditional agriculture is impossible. Plants need light for photosynthesis. That's non-negotiable. But artificial light can substitute for sunlight, and plants don't actually care whether photons come from the sun or from an LED, as long as the wavelength is right. This is hydroponics, growing plants in nutrient-rich water under artificial light. It's not a new technology. We've been doing this for decades. What changes in a survival scenario is the scale. You'd need vast hydroponic facilities, kilometres of growing chambers, thousands of LED arrays, all powered by geothermal electricity. The advantage of hydroponics is efficiency. Without soil, you can stack growing beds vertically, maximising space. Without weather or pests or diseases from the surface world, yields are consistent and predictable. Without seasons, you can harvest year-round. A hydroponic farm, properly managed, can produce far more food per square metre than traditional agriculture. The crops would be chosen for caloric efficiency and growth speed. Potatoes are excellent. High in calories, grow relatively quickly, tolerable of less than ideal conditions. Soybeans provide protein and fat. Leafy greens like lettuce and spinach grow fast and provide vitamins. Tomatoes are surprisingly productive in hydroponic systems. Grains like wheat and rice are possible but less efficient. They take longer to grow and require more space. You'd need a balanced diet, of course. Human nutrition requires proteins, carbohydrates, fats, vitamins, minerals. A diet of just potatoes would keep you alive. Just ask the Irish during certain unfortunate periods of their history, but wouldn't keep you healthy long term. So you'd need variety. Multiple crops, carefully managed, providing complementary nutrients. And you'd need the light spectrum right. Plants use different wavelengths for different processes. Blue light promotes vegetative growth. Red light triggers flowering and fruiting. A proper grow light needs both, plus some green wavelengths that plants reflect, which is why they look green to us, but still use in small amounts. Modern LED grow lights can be tuned to provide exactly the spectrum plants need. Nothing wasted on wavelengths they don't use. It's more efficient than sunlight in a way, though vastly more expensive in terms of energy input. Speaking of energy, this is the constraint. Growing food with artificial light requires a lot of electricity. The sun provides this energy for free. Without the sun, you're paying for every photon. It takes roughly 400 watts of LED lighting per square metre of growing space to match the usable light plants would get from sunlight. Scale that up to feeding a population, and you're talking megawatts, gigawatts of power devoted just to food production. This is why geothermal energy is so critical. You need a reliable, constant, large-scale power source. Geothermal provides that. It's not unlimited. There's only so much heat you can extract from a given volume of rock. But it's sufficient for a reduced population living efficiently. Protein is trickier than carbohydrates. Plants can provide protein, soybeans, lentils, chickpeas, but humans are traditionally omnivorous, and a purely plant-based diet requires careful planning to get all essential amino acids. So you'd want animal protein too. Fish are the obvious choice. Aquaculture, fish farming works well in controlled environments. Tilapia are nearly ideal. They grow fast, tolerate a wide range of conditions, reproduce readily, and convert feed to body mass efficiently. You'd need tanks, filtration systems, temperature control, but these are solvable engineering problems. Feed the fish with the waste products from the hydroponic systems. Plant trimmings, roots, anything not suitable for human consumption. The fish eat the plant waste, you eat the fish, and the fish waste becomes fertilizer for the hydroponic plants. It's an elegant closed loop called aquaponics. Waste from one system becomes input for another. Nothing is wasted because nothing can be wasted. Insects are another protein source. Crickets and mealworms are incredibly efficient. They convert feed to body mass at ratios that make fish look wasteful and cattle look absurd. They require minimal space, they reproduce quickly, they're high in protein. But the main barrier is cultural. Many societies don't traditionally eat insects, but in a survival situation, cultural preferences become less important than calories. You'd probably grind them into flour or paste rather than eating them whole. Mix cricket flour into bread, and it's just protein-enriched bread. Most people could adjust to that, especially if they've never known anything else. The younger generations born underground wouldn't have our cultural baggage about eating bugs. To them, it would just be food. Water is straightforward, actually. It seems like it would be a problem, but it's not. You have vast amounts of water frozen on the surface. You collect ice, melt it with waste heat from power generation, filter it, and use it. The melted ice is clean. The cold kills pathogens, and freezing tends to separate out impurities. So you actually get purer water than you would from surface sources in the old world. The challenge is recycling. In a closed underground system, every drop of water needs to be reclaimed. Wastewater needs to be filtered and purified. Humidity needs to be condensed from the air. Metabolic water from respiration needs to be captured. Nothing can be lost because there's no rain to replenish supplies. This sounds daunting, but we already do this on the International Space Station. Astronauts drink recycled urine, and they're fine with it because it's been purified to standards far exceeding normal tap water. The same technology scales up. It's just a matter of building enough filtration capacity. Air is similar. You need oxygen, obviously. Plants produce oxygen through photosynthesis, and if you have enough hydroponic farms, they produce enough oxygen for your population. It's a closed loop. Humans breathe oxygen and exhale carbon dioxide. Plants take in carbon dioxide and release oxygen. The cycle continues. You'd need backup systems, of course, chemical oxygen generators that can produce O2 from water if the plants can't keep up, scrubbers to remove excess CO2 if needed, filtration to remove other contaminants, volatile organic compounds, particulates, whatever else accumulates in recycled air. But again, this is known technology. Submarines do this, spacecraft do this, it scales. The psychology of confinement is perhaps the hardest challenge, and it's not really a technology problem. Humans evolved in open spaces. We're savanna apes, used to horizons and sky and long sightlines. Put us in tunnels and enclosed spaces for our entire lives, and something in our psyche rebels. This is real. Submarine crews, astronauts, Antarctic researchers, people who spend extended time in confined spaces, they all deal with psychological effects, depression, anxiety, interpersonal conflict. The human mind needs variety, stimulation, some sense of space and freedom. The solution, probably, is a combination of design and distraction. Design spaces to feel as open as possible, high ceilings, large common areas, careful lighting that simulates natural patterns, brighter during day hours, dimmer during night, even though these are arbitrary. Murals and artwork depicting outdoor scenes, virtual reality environments where you can experience simulated nature, and distraction in the form of purpose. People need meaningful work, need to feel like they're contributing to something important. In a survival civilization, this isn't hard to provide. Everyone's work literally keeps civilization alive, but it needs to be acknowledged, celebrated, made clear. You're not just maintaining a water filter, you're ensuring your community's survival. That matters. That gives meaning to labor that might otherwise feel tedious. Community is crucial. In confined spaces with limited population, every person matters. Social bonds need to be strong. Conflicts need to be resolved quickly. You can't afford grudges when you're living in close quarters with the same few thousand people for your entire life. So you develop social structures that prioritize harmony, cooperation, collective well-being, not because you're utopian idealists, but because the alternative is social collapse. This is the science and engineering of survival. It's not simple. It's not easy. It requires solving dozens of interlocking technical challenges, maintaining complex systems, and keeping people psychologically healthy in conditions we're not evolved for. But it's possible. None of it violates physics. None of it requires technology we don't have or couldn't develop. It's just engineering at scale, done carefully, with everything working together. We could do it if we had to. We could survive underground, powered by Earth's own heat, growing food in artificial light, recycling everything, creating a closed-loop civilization that doesn't need the sun. Would it be comfortable? Not particularly. Would it be what we'd choose? Absolutely not. But would it work? Yes, it would work. And somehow, that's both reassuring and unsettling. Reassuring because it means we're not as fragile as we might fear. Unsettling because it means we could lose so much: the sun, the surface, the natural world, and still technically survive. But survival is something. When the alternative is extinction, survival is everything. The science supports it. The engineering is feasible. The will to live would provide the rest. We'd survive, we'd adapt, we'd continue. Because that's what life does. It finds a way, always. We've talked about the physics, the engineering, the biology of survival. We've covered geothermal wells and hydroponic farms and closed-loop life support systems. But humanity isn't just a collection of technical problems to be solved. We're storytellers, meaning makers. We need more than food and air and warmth. We need culture, we need art, we need stories that help us understand who we are and where we came from and why any of it matters. So let's talk about what happens to human culture in permanent darkness. What stories do we tell ourselves when the sky is gone and the sun is just a memory? The first generation, the people who remember the sun, would be historians by necessity, witnesses to a lost world. Every person who felt sunlight on their face, who saw a blue sky, who experienced weather and seasons and the natural world, becomes a living archive. Their memories are precious beyond measure, because once they're gone, direct knowledge of the surface world disappears with them. These survivors would tell stories constantly, to their children, to their grandchildren, to anyone who would listen. I remember mornings. I remember how the sun would rise slowly, painting the sky pink and orange before settling into blue. I remember warmth that came from above, not below. I remember rain, actual water falling from the sky, can you imagine? I remember wind, invisible but real, pushing against you as you walked. The children would listen, transfixed, not entirely understanding perhaps, but hungry for these glimpses of something they'll never experience. What's a cloud like? What's grass feel like under your feet? What's the difference between sunlight and LED light? Why did people say summer was better than winter? What was a sunset? And the survivors would try to explain and fail, because some experiences don't translate. How do you describe the warmth of sunlight to someone who's only known geothermal heating? How do you capture the precise quality of natural light, the way it changes through the day, the particular glow of golden hour? Language fails. You end up using metaphors, and the metaphors get less precise with each retelling, and eventually the truth blurs into approximation, blurs into myth. By the second generation, the stories start to change. The children who grew up underground, who only knew the surface from their parents' stories, would retell those stories to their own children. But memory of memory is less precise than memory. Details shift, exaggerations creep in. The sun becomes brighter in the retelling. The sky becomes bluer. Nature becomes more beautiful, more perfect. because nostalgia always improves what it remembers. My grandmother told me about trees, not like our plants in the growing chambers, huge, bigger than buildings, with branches that reached up to touch the sky, and leaves that would change colour with the seasons. Green, then yellow, then orange, then red, then they would fall to the ground like snow. Can you imagine? Plants that deliberately shed parts of themselves and grew them back every year. My grandfather told me about oceans. Water, more water than you could see across, stretching to the horizon. And it would move, waves, he called them, constantly rolling and crashing against the shore. And it was salty, too salty to drink, filled with creatures that swam through it like we walk through air. Fish larger than a person, whales larger than a train, all living in water, breathing water, never seeing the surface or the sky. These stories become treasured, passed down, embellished. The surface world becomes mythological. Eden, paradise, lost. The place where humans were meant to live before the catastrophe, before the sun disappeared and the world ended and we retreated underground to survive. And with that mythology comes meaning-making, because humans can't just accept that bad things happen randomly. We need explanations. We need reasons. We need someone or something to blame, or thank, or pray to. Religious interpretations would emerge immediately. Some would say the disappearance of the sun was divine judgment. Humanity sinned, took the sun for granted, damaged the earth, lost touch with nature or God or cosmic harmony, and this is punishment. The underground existence is penance. Redemption might come if we're worthy, if we learn our lessons, if we change our ways. Others would say the opposite. The sun didn't abandon us. We were given the tools to survive its loss. The geothermal heat, the intelligence to engineer solutions, the determination to continue. These are gifts. The underground isn't punishment, but transformation. A test, perhaps, a chrysalis. We're becoming something new, something stronger, something that doesn't need a sun to thrive. Still others would reject religious explanations entirely. The sun disappeared, if it even existed, and maybe it was always myth, maybe it was metaphor for something else. And humanity adapted, because that's what life does. No divine plan, no cosmic meaning, just survival, just adaptation, just the stubborn refusal to die. That's its own kind of faith, really. Faith in human capability, in our own agency, in the possibility that we don't need higher purpose to justify our existence. These interpretations would coexist, clash, evolve, denominations would form, sects, schisms over details. Did the sun disappear at noon or dawn? Does it matter? What were its last words? No, stars don't speak, but maybe metaphorically. Should we pray for its return? Should we pray to it? Is it even listening? Meanwhile, secular culture would develop its own relationship with the lost surface. Literature about the sun would become its own genre. Historical fiction set in the bright world. Romances where characters experience impossible things like picnics and beaches and watching clouds drift by. Adventures in the old world exploring forests and mountains and deserts that no longer exist as anything but frozen wastelands kilometers above. Some of this literature would be scrupulously researched, based on surviving records and photographs and the testimonies of those who remember. These would be treasured as glimpses of truth, educational texts as much as entertainment, ways to understand what was lost. Other literature would be pure fantasy, authors who never saw the surface, writing about it from imagination, getting details wildly wrong but capturing something emotionally true, the sun as a character, as a god, as a metaphor, nature as Eden, or as adversary, the surface as paradise, or as something humans were right to leave behind, a harsh, dangerous place that we've improved upon with our controlled underground world. There would be poetry, obviously. So much poetry. Elegies for the lost sun, meditations on darkness and light, metaphors about what it means to live in shadow, celebrations of artificial things, LED light, recycled air, synthesized food, finding beauty in the human-made, in survival, in our capacity to create meaning even in constrained circumstances. Music would thrive. You don't need a visual environment for music. Sound works the same underground as it did on the surface, and in some ways the underground is better for music. Carved chambers with perfect acoustics, spaces designed specifically for sound. No competing noise from wind or rain or distant traffic, just silence, broken by whatever music humans choose to create. The instruments would change, maybe. Wind instruments require careful breath control, and in a sealed environment with recycled air, that becomes medically relevant. You can't have everyone hyperventilating with didgeridoos when the CO2 scrubbers are running at capacity. So maybe wind instruments become less common, electronic instruments more prevalent. Synthesizers can do anything, create any sound, limited only by imagination and the electrical grid. The songs would be about what songs are always about: love, loss, hope, fear, belonging, alienation, joy, despite circumstances, sorrow, despite success. The human emotional range doesn't change just because the environment does. We'd still fall in love in the tunnels, still grieve deaths, still celebrate births, still feel lonely in crowds and connected to strangers and all the complicated, messy emotions that make us human. Visual art would be strange. How do you paint landscapes when you've never seen one? How do you capture light and shadow when you've only known flat LED illumination? Some artists would work from photographs and videos, trying to recreate what was. Others would give up on representation entirely, working in abstract forms, exploring colour and shape and composition without any reference to the natural world. There might be an entire artistic movement based on texture. In the underground, where everything is rock and metal and artificial materials, texture becomes important. Rough and smooth, hard and soft, the tactile dimension of art, things you experience through touch as much as sight. Sculptures designed to be explored by hand, murals with different surfaces, art that acknowledges the confined space, the constant contact with walls and surfaces, the way underground life is more tactile than the open surface world ever was. And there would be art about absence, about negative space, about what's missing, empty frames representing windows that don't exist, blank canvases titled Sky, sculptures with holes where the sun would be, art that makes you aware of what you don't have by marking the space it would occupy. Children born underground would create their own culture, of course, not based on nostalgia for the surface. They have no nostalgia for something they never knew, but based on their actual experience. Games played in tunnels, stories about underground adventures, heroes who excel at the skills that matter in this world, engineering, hydroponics, social harmony, problem solving. They'd have their own slang, their own references, their own shared experiences that the older generations couldn't fully understand. Growing up in eternal darkness would seem normal to them. Artificial light would seem natural. The idea of sky would seem strange, unnecessary, maybe even frightening. What do you mean there's nothing above you? Just infinite empty space? That sounds terrifying. I prefer solid rock, thank you. Education would be crucial. Not just technical education, how to maintain the life support systems, how to grow food, how to fix the water recyclers, but cultural education. History, literature, article, music, the things that make us human beyond mere survival. Because if you lose culture, if you reduce existence to just staying alive, you lose something essential. You survive, but you don't live. And there's a difference. So the schools would teach engineering and botany, yes, but also poetry and history. They teach about the sun not as a technical fact, but as a cultural touchstone. They teach about seasons and weather and the natural world, not because students would ever experience these things, but because they're part of human heritage, part of who we are, part of the story we tell about ourselves. And maybe in some distant classroom, a teacher would tell students about thought experiments, about how imagining impossible scenarios helps us understand real principles, about how asking what if leads to insights about what is. What if the sun disappeared, the teacher might ask, and the students who live in the answer to that question might not immediately see the point, but gradually, through discussion, they'd understand. The thought experiment isn't about catastrophe. It's about appreciation, about understanding what matters, about recognizing that the world we have, even this underground world, this constrained existence, is precious because it's what allows us to continue. The stories we tell in the dark aren't just about the light we lost. They're about the light we carry with us. The internal light of consciousness, creativity, connection, the light that no disappearing sun can take away because it was never the sun's to give. It's ours, uniquely human. The ability to find meaning in darkness, to create beauty in confined spaces, to tell stories that help us understand ourselves and each other. We're storytellers. That's what we are, that's what we've always been. And no amount of darkness, no amount of loss, no amount of catastrophe can take that away. As long as there are humans, there will be stories. Stories about where we came from, stories about who we are, stories about where we might be going. Stories about the sun, yes, but also stories about the dark, about survival, about adaptation, about finding light in the most unlikely places. And those stories, perhaps, are the most important light of all. And so we come to the end of our journey. We've travelled through an impossible scenario together, watched the sun disappear, followed humanity underground, explored survival across centuries and millennia, and discovered what we might become in permanent darkness. We've walked through catastrophe and adaptation, through loss and resilience, through the physics of survival and the poetry of meaning-making. But now it's time to come back to reality, back to the light. Because here's the truth we've known all along, but needed this journey to fully appreciate. The sun is still there. Right now, as you listen to these words, the sun is doing exactly what it's always done. Fusing hydrogen into helium, radiating energy across 93 million miles of space, warming Earth's surface, driving weather patterns, making photosynthesis possible, sustaining the vast web of life that includes you, me, every person, every plant, every creature that depends on this remarkable star. It's still there, faithful, constant unchanged by our imagination of its absence. Tomorrow morning it will rise, not because we deserve it or earned it or did anything to make it happen, just because that's what stars do. They shine, they burn, they give light and warmth to any planets fortunate enough to orbit at the right distance. And we are fortunate, cosmically, impossibly, miraculously fortunate. We spent all this time imagining what would happen without the sun, and the point, the real point, was never about the darkness. It was about appreciating the light we have, about noticing what we usually ignore, about recognizing that this moment, right now, with the sun faithfully burning, and Earth faithfully orbiting, and life faithfully continuing, This is the gift. This is what matters. So maybe tomorrow, when you wake up, you'll pay attention to the light, not in some profound spiritual way, though if that's your inclination, go for it. But just notice it. Notice how it changes through the day, how morning light feels different from afternoon light, how shadows move, how colours look different under natural light than under artificial light, how there's warmth that comes from above, from that fusion reaction 93 million miles away, reaching across the void to touch your face. Maybe you'll step outside for a moment, feel actual sunlight, stand in it deliberately, consciously, aware that you're experiencing something that's been happening on this planet for 4.5 billion years, that every ancestor you have, every human who's ever lived, has stood in this same light, that you're connected to them through this experience, through this shared gift of a star that gives without asking anything in return. Or maybe you won't. Maybe tomorrow will be cloudy, or you'll be busy, or you'll forget because that's what we do. We forget to notice the everyday miracles because they are everyday. And that's okay too. This isn't about achieving perfect gratitude for every moment. It's just about, occasionally, when you remember, taking a second to acknowledge, the sun is there. I am here. We exist together in this particular moment, in this particular arrangement of matter and energy, and that's pretty remarkable when you think about it. We've learned some things on this journey. We've learned about Earth's resilience, how even without the sun, the planet continues, the core stays hot, life finds a way in the deep places. We've learned about human adaptability, how we could survive in conditions we're not designed for, if we're clever enough and determined enough. We've learned about geothermal energy and hydroponics and closed-loop life support systems, and all the technical details of surviving the impossible. But more than that, we've learned about perspective, about understanding our place in the universe, about holding two truths simultaneously, that we're cosmically insignificant, just one species on one planet orbiting one ordinary star in one galaxy-typical galaxy among hundreds of billions, and that we matter enormously, at least to ourselves, at least in this moment, at least in the local context of human experience and consciousness and care. We've learned about impermanence, about accepting that everything ends, even things that seem eternal. The sun will die 5 billion years from now. Our civilization will end, probably sooner than that. Our species will go extinct eventually. All species do. You and I will die, much sooner still. None of it lasts forever, and somehow that's okay, because the impermanence doesn't negate the meaning. It might even create it. Things matter because they're temporary. Moments are precious because they pass. We've learned about adaptation, about how life, especially human life, is remarkably flexible. We can survive in a wider range of conditions than we might assume. We're not as fragile as we fear, but we're also not as invulnerable as we might hope. We need specific conditions to thrive, even if we can survive in others. And the difference between surviving and thriving is worth paying attention to. And we've learned about gratitude, about how imagining loss helps us appreciate what we have, about how thought experiments aren't just intellectual exercises, they're tools for understanding, for perspective taking, for seeing our actual reality more clearly by contrasting it with an imagined alternative. The sun didn't disappear. It won't disappear. But we imagined it did. And now, coming back to reality, maybe we see our star a little differently. Maybe we appreciate it a little more. Maybe we understand, in a way we didn't before, just how dependent we are on this particular ball of fusing hydrogen, how lucky we are that it exists, how precious is every moment we get to live under its light. That's worth something, isn't it? That shift in perspective, that deepening of appreciation, that moment of recognizing what you usually take for granted. So here we are, at the end of our journey through imagined darkness, returning to actual light. The sun is still shining, Earth is still spinning, life is still thriving in conditions that are, cosmically speaking, quite rare and quite special. The same conditions that existed before we started this thought experiment. Nothing has changed in reality, but maybe something has changed in how we see reality. Maybe just for a moment we see it more clearly, more gratefully, more aware of what we have, what we might lose, what we should cherish while it lasts. And if this thought experiment has given you that moment of clarity, that shift in perspective, that increased appreciation for the star that makes everything possible, then it was worth the journey through impossible darkness. The sun will rise tomorrow, and the day after that, and for billions of days to come. It's not going anywhere, not for 5 billion years at least, and 5 billion years might as well be forever on any time scale that matters to us. So rest easy, sleep peacefully, dream of sunlight if you like, or dream of anything else, or simply drift into that darkness that's different from the darkness we explored, the darkness of rest, of sleep, of your mind letting go of conscious thought and finding its own strange paths through the night. And when you wake, whenever that is, wherever you are, the sun will be there, waiting, shining, giving light and warmth and life to this small blue world we call home. Still there, still faithful, still ours. Thank you for traveling with me through this impossible scenario. Thank you for imagining the unimaginable, for exploring the darkness, for following this thought experiment through to its end. I hope you found something useful in it, something meaningful, something that changes even slightly how you see the ordinary miracle of our star. If you've enjoyed this exploration, I'd be ever so grateful for a gentle like and subscribe to join me for more cosmic journeys and to help others discover these late-night wanderings through space. This is the Sleepy Astronomer, wishing you good night wherever you are. May you dream well under your faithful star, and may you wake to light